In the vast, star-speckled tapestry of the cosmos, spiral galaxies swirl like celestial pinwheels, beautiful, structured, and familiar. We know the shape, graceful arms winding out from a bright central bulge, brimming with stars, gas, and dark matter. Our own Milky Way is one of them, and for much of human history, galaxies like it have defined our understanding of how the universe organizes itself. But what if some spiral galaxies aren't just picturesque? They're monsters cloaked in elegance. What if some break the limits of mass, brightness, and structure, while still retaining the familiar spiral form? Welcome to the realm of super-spiral galaxies, a class so extreme, so luminous, so massive, that they defy every cosmic expectation. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine a galaxy so large that it could swallow the Milky Way whole, 10 times over. Imagine it spinning at such incredible speeds that, by all logic, it should tear itself apart, and yet, it remains calm, poised, and almost unnaturally organized. These aren't just theoretical constructs or distant mathematical curiosities. They are real, rare, and awe-inspiring. They emit light on a scale that rivals quasars, those ancient beacons powered by voracious black holes. But unlike quasars, these galaxies aren't chaotic remnants of early galactic violence. They're fully formed spirals, structured and serene. The story of super-spirals is more than just astronomical trivia. It's a tale that challenges how we understand galaxy formation and evolution. For decades, scientists believed that as galaxies grew larger and older, they would gradually shed their structure and transform into elliptical blobs, featureless, red, and done forming stars. But super-spirals laugh in the face of that expectation. They're not only vast and ancient, they are alive with furious star formation, dynamic rotation, and incredible energy output. They aren't the relics of the early universe. They're ongoing cosmic phenomena, rare, yes, but profoundly revealing. And the mystery runs deeper. These galactic juggernauts are not supposed to exist in their current form, yet they do. They shouldn't be able to spin this fast, shine this bright, or remain this structured without tearing themselves apart or collapsing into ellipticals. Their very existence breaks the rules of cosmic architecture we thought we understood. They aren't just bigger, faster, or brighter, they're wrong in the most fascinating ways. So what exactly are they? Where did they come from? How are they powered? What secrets do they hold about dark matter, star formation, and the early universe? Could they harbor life? Could they be the final form of some galaxies? Or merely a brief, dramatic phase? And perhaps most intriguingly, what does their existence mean for our own Milky Way's future? As we begin this journey into the heart of these cosmic behemoths, prepare to see galaxies not as peaceful, swirling gardens of stars, but as rebellious titans that have carved their own paths through the universe. This is not just a story about size, it's a story about survival, power, and elegance. Super-spirals remind us that in a universe ruled by entropy, some structures don't just endure, they thrive. Before we can appreciate how extraordinary super-spirals are, we need to understand what they're built upon, the structure of a classic spiral galaxy. These are among the most iconic and visually stunning structures in the cosmos. They make up roughly 2/3 of all observed galaxies in the nearby universe, forming graceful, swirling disks that stretch across hundreds of thousands of light-years. At the heart of every spiral galaxy lies a central bulge, a tightly packed cluster of older stars, often reddish in hue, surrounded by a supermassive black hole. This bulge is usually spheroidal and composed of ancient stars that no longer form in large numbers, relics from the galaxy's formative years. It serves as a gravitational anchor for the entire galactic system, housing billions of suns and sometimes even a bright active nucleus if the black hole at the center is still feeding. Extending outward from this bulge are the spiral arms, the most recognizable feature. These arms are not rigid structures but rather regions of enhanced density waves, where gas and stars cluster together temporarily as they orbit the galactic center. As gas clouds enter these regions, they become compressed, triggering waves of star formation. This is why spiral arms often appear bright and blue. They are lined with hot, massive, short-lived stars that light up the surrounding regions. The arms themselves spiral outward like cosmic whirlpools, often winding 2 or more times around the core, forming structures that can be tight and symmetrical or loose and flocculent. These patterns are determined by the galaxy's internal dynamics, including the rate of rotation and distribution of matter. Between the arms lies a flatter, less structured disk composed of older stars, gas, and dust, a calm sea surrounding the violent star-making factories of the arms. Encasing the entire structure is a dark matter halo, an invisible yet immense bubble of gravitational influence that helps hold the galaxy together. Without this mysterious dark scaffold, the galaxy would fly apart under its own rotation. Dark matter outweighs all the stars and gas in the galaxy several times over, and while we can't see it, we can trace its presence by observing how the stars move, especially in the outer regions. Then there's the galactic disk itself, a thin, vast plane that defines the galaxy's primary shape. Within this disk, the bulk of star formation occurs. Interstellar gas clouds drift through space, colliding, collapsing, and birthing stars in an ongoing cycle. The disk is also where the galactic arms reside, as well as large-scale features like bars, straight or curved bands of stars that stretch from the center into the disk, often acting as channels that funnel gas toward the core. Spiral galaxies come in many subtypes, classified by the tightness of their arms, the size of their bulge, and the presence of a bar. From SA to SC, or SB for bar types, this classification helps astronomers understand how structured or chaotic a spiral galaxy might be. But even the largest of these, including our own Milky Way, pale in comparison to what happens when a spiral galaxy breaks the rules entirely. Because while spiral galaxies are typically thought of as moderate in size and actively forming stars, they are still expected to follow certain limits. Their structure is balanced, held together by a dance between gravitational collapse and centrifugal force, between star birth and stellar death. The interplay between these processes results in a steady state, dynamic, but predictable. Until something extraordinary happens. Until a spiral galaxy doesn't just grow, it supercharges. And that's where the story begins to shift. Because not all spirals stay within the bounds of moderation. Some expand far beyond what models predict. Some spin faster than physics says they should. Some shine brighter than quasars, without tearing themselves apart. These are not typical spirals. They are something else entirely. In 2015, the cosmic conversation around spiral galaxies changed dramatically. A team of astronomers, digging through data from the Sloan Digital Sky Survey (SDSS), stumbled upon something unexpected: a handful of spiral galaxies that were simply too big, too bright, and too massive to fit the mold. They were shaped like ordinary spirals, yes, disks, arms, central bulges, but their size and luminosity were in a different league altogether. These weren't just large galaxies. They were super spirals. The name wasn't hyperbole. These objects stood apart from the tens of thousands of galaxies catalogued before. Where a typical spiral galaxy might span 100,000 light-years and contain a few 100 billion stars, some of these new discoveries extended over 400,000 light-years across and held more than 1 trillion stars. That's not just scaling up, it's leaping across the known bounds of galactic structure. Super spirals don't just stretch across vast distances. They radiate energy at levels that rival quasars, the ancient and hyperluminous cores of young galaxies powered by feeding black holes. And yet, unlike quasars, super spirals aren't chaotic. They're not smothered in radiation from a violent central engine. They shine from the collective light of countless stars, stars that are actively forming, burning, and evolving across their disks. In fact, these galaxies are sometimes even more luminous than quasars, without the same destructive intensity. This combination of characteristics, extreme mass, high star formation, immense brightness, and preserved spiral structure, was so unusual that astronomers were forced to define a new class. These weren't elliptical giants or spiral elders. They were ultraluminous spiral galaxies on steroids. Thus, the term superspiral was born, and with it, an entire category of celestial phenomena that redefined the upper limits of spiral evolution. The concept of a superspiral isn't just about grandeur. It challenges long-standing assumptions in astronomy. For decades, it was accepted that the most massive galaxies in the universe, the ones with trillions of stars, must be elliptical. These galaxies typically form through violent mergers, collisions that destroy the fragile spiral architecture and create smooth, football-shaped remnants. So when astronomers found spiral galaxies as massive as the biggest ellipticals, and yet still orderly and intact, it was more than surprising. It was paradigm-breaking. Superspirals are not theoretical outliers either. They're confirmed objects. Astronomers have now identified several dozen across the observable universe. Most of them exist at distances of hundreds of millions to a few billion light-years away, which means we see them as they were in the relatively recent cosmic past. They're not fossils of the early universe. They're contemporaries of the Milky Way, yet far more intense and evolved. Their star formation rates are staggering, dozens to hundreds of solar masses per year, compared to just a few for our galaxy. Their gas reservoirs are vast, their spin rates are ferocious, and their gravitational influence stretches far beyond what most simulations predicted. And yet, through all this, they remain visually recognizable as spirals, albeit enormous ones, as if someone had taken the Milky Way and dialed every parameter to the maximum. What makes superspirals even more intriguing is their diversity. Some have massive bars crossing their centers. Others display flocculent, patchy arms. A few exhibit nearly perfect symmetry, as if painted with a cosmic compass. Despite their massive sizes and blistering star birth rates, many of them maintain clean, well-organized structures, without signs of violent disruptions or mergers. This defies what we'd expect from a galaxy this active. Somehow, they are both chaotic in energy and serene in appearance. It's this tension, between the expected and the observed, that makes superspirals so fascinating. They sit at the extreme end of almost every measurable galactic scale: size, brightness, star formation, spin rate, and mass. And yet, they retain a form we thought couldn't survive such extremes. In doing so, they force astronomers to re-examine the equations and models that describe how galaxies grow, evolve, and die. Superspirals aren't just bigger versions of normal galaxies. They are fundamentally different, not only in quantity but in quality. Their very existence pushes the boundaries of galactic physics. They are exceptions that demand explanation, and in doing so, they offer new clues about the nature of cosmic structure, the role of dark matter, and the forces that sculpt the visible universe. To grasp the enormity of superspirals, let's use a familiar benchmark: our own Milky Way. It's an impressive galaxy in its own right, stretching about 100,000 light-years in diameter. If you could travel at the speed of light, 300,000 kilometers per second, it would still take you an entire human lifetime to cross from one end of the Milky Way to the other. And yet, compared to the colossal scale of some superspirals, the Milky Way begins to look modest. Superspiral galaxies can be over 10 times larger in diameter than the Milky Way. Some span over 450,000 to 500,000 light-years across. That's not just astronomical in the casual sense, it's nearly beyond comprehension. Imagine laying 10 Milky Ways side by side in the sky, each packed with stars, gas, dust, and dark matter. These superspirals are cosmic leviathans, sprawling disks of matter and energy that dominate the space around them on a galactic scale. And their vastness isn't empty space. These aren't thin, wispy structures just barely clinging together at the edges. No, the arms of these galaxies are brimming with active star formation, thick concentrations of gas and dust, and complex stellar populations that span billions of years in age. Even in their outer regions, where ordinary galaxies tend to fade into ghostly halos, superspirals remain active, structured, and bright. This immense size raises an important question: how does a galaxy get so big in the first place without tearing itself apart or collapsing inward under its own gravity? Galactic growth is usually a slow and violent process. Galaxies merge. They cannibalize smaller neighbors. They grow denser and hotter, often losing the delicate spiral pattern in the chaos. But superspirals somehow sidestep this trajectory. They continue to grow and accumulate matter while preserving their swirling order. One possibility lies in their incredible mass. These galaxies can weigh in at several trillion solar masses, including stars, gas, dust, and especially dark matter. That's enough mass to stabilize a galactic disk against many of the forces that would normally warp or destroy it. Their vast dark matter halos serve as cosmic scaffolding, keeping the structure coherent even at scales that would normally fragment under gravitational stress. But size isn't just about mass, it's also about time. Superspirals likely had unusually quiet evolutionary histories. Unlike the Milky Way, which had multiple disruptive mergers in its past, these galaxies may have grown more gradually, through steady accretion of gas and minor interactions that didn't disturb their overall shape. Over billions of years, this quiet growth allowed them to build massive disks without losing their spiral arms or structural symmetry. The outer edges of these giants can also harbor features rarely seen in smaller galaxies: extended arms that stretch far into intergalactic space, wrapping around the galaxy like wisps of luminous fog. These regions aren't just barren outposts. They are sites of ongoing star formation, fueled by massive reservoirs of gas pulled in from the surrounding cosmic web. The sheer scale means that even the peripheries of superspirals can outshine entire dwarf galaxies. And the size has implications for rotation as well. These galaxies don't just sprawl, they spin. Their rotational velocities can exceed 500 kilometers per second, more than double that of the Milky Way. Maintaining coherence across such vast distances while rotating so rapidly is a feat that has puzzled astronomers. Something is helping these structures stay in balance, and that something might very well be dark matter playing an even greater role than we thought. Even their galactic bulges, the dense central regions, can be up to 10 times the size of the Milky Way's core. These central zones act as gravitational engines, regulating the orbits of stars and the spiral arms. And in some superspirals, those arms extend in beautifully symmetrical patterns for hundreds of thousands of light years, as if etched by a steady, unseen hand across the darkness. To put it another way, if the Milky Way is a city, superspirals are continents. Their disks could engulf not just our galaxy, but the entirety of the local group, the collection of nearby galaxies including Andromeda, Triangulum, and dozens of dwarfs. They are galaxies of galaxies, bound within a single spiral form. Their size doesn't just stretch space, it stretches our models. It suggests that under the right conditions, spiral structure can be preserved even at unimaginable scales. That there are pathways to growth that don't always end in disorder. That the cosmos, even at its largest and brightest, can still spiral with elegance. What truly pushes superspirals into the realm of the extraordinary isn't just their size, it's their light. These galaxies don't just glow, they blaze with a brilliance so intense, it challenges the very classification of what a galaxy is. Some superspirals radiate more light than quasars, those distant, supermassive black hole-powered beacons that were long considered the brightest objects in the universe. But here's the twist: unlike quasars, which shine from the concentrated fury of a central core, superspirals shine from across their entire disk. Their brilliance is not centralized, it is distributed. In fact, some superspirals produce over 100 trillion times the luminosity of the Sun. To put that in perspective, the Milky Way, with all its hundreds of billions of stars, clocks in at around 10 billion solar luminosities. Superspirals are orders of magnitude brighter, yet they maintain a stable spiral shape, a star-forming disk, and a relatively peaceful appearance. It's as if someone took the concept of a galaxy, cranked up the brightness to an unthinkable level, and yet somehow didn't melt the structure. This immediately presents a puzzle. Where is all that light coming from? Quasars shine because matter falls into a central black hole and is converted into radiation through extreme gravitational compression. Superspirals, on the other hand, generate their light through normal stellar processes, albeit on a scale that is anything but normal. They don't cheat with a single light bulb in the middle. They light up the room with trillions of candles all at once. Much of their luminosity comes from intense star formation. These galaxies are producing stars at rates as high as 50 to 100 solar masses per year, sometimes even more. Compare that to the Milky Way, which adds only about 1 or 2 new stars per year. That's like comparing a quiet suburban neighborhood to a neon-lit metropolis in full construction mode, building skyscrapers every minute. Massive, hot, young stars, especially O and B types, flood their surroundings with ultraviolet and blue light, which contributes significantly to their overall brightness. These stars don't live long, but while they burn fiercely. And it's not just the number of stars forming, it's the sheer number of stars already formed. With stellar populations often exceeding 1 trillion stars, even the older, cooler stars contribute a massive baseline luminosity. When you combine that with ongoing rapid star formation, you get a compound effect, old stars providing volume, new stars providing intensity, and the result is a galaxy so luminous it can be seen from billions of light years away. Interestingly, their brightness doesn't just challenge our visual understanding, it messes with our classification systems. Galaxies this bright, in traditional thinking, should fall into extreme categories: starburst galaxies, merging systems, or AGN-dominated monsters. And yet, superspirals defy all those boxes. They are not short-lived explosions. They are not torn apart by mergers. They are not obliterated by a raging black hole at the center. They are stable, structured, and self-illuminated. In essence, they are natural light factories operating at peak cosmic efficiency. This puts pressure on traditional luminosity curves, the relationships between a galaxy's size, mass, and light output. Superspirals exist far above the normal lines on these charts. They break the scale. They don't fall into any neat category of the Hubble sequence. They are outliers, and that makes them powerful tools for studying the limits of galaxy formation physics. One might wonder, could an AGN still be responsible for part of their brightness? After all, many massive galaxies harbor active galactic nuclei. And yes, in some cases, there may be modest contributions from a central supermassive black hole. But what makes superspirals stand apart is that their light is not dominated by their core. Their disks shine just as brightly, sometimes even more. This uniform luminosity across such vast spans implies a self-sustaining engine of star formation and energy output, one that doesn't rely on the violent processes seen in quasars. It also raises the question, how do these galaxies sustain such activity without burning out? Quasars have lifespans of perhaps tens of millions of years. But superspirals appear to have lasted far longer. Their continued brightness, sustained across billions of years, means they must be incredibly efficient at pulling in fresh gas, converting it to stars, and radiating light without descending into the instability that would shatter their structure. This kind of long-term, galaxy-wide luminosity is almost unheard of, and it's why some astronomers consider them not just anomalies, but keys to understanding the upper boundaries of galactic life. And it's not just about their own illumination. From a distance of billions of light years, their glow cuts through cosmic dust, intervening galaxies, and the blackness of space itself. They are lighthouses in the night, their glow not just stunning, but useful. Observing them helps scientists trace the evolution of large-scale structure in the universe, probe dark matter distributions, and refine models for galaxy growth in ways that no average galaxy can. In a universe where most bright objects burn fast and die young, superspirals stand as radiant exceptions, long-lived, brilliantly lit, and completely unexpected. They are not supposed to shine like quasars. And yet they do, not from chaos, but from cosmic mastery. If the sheer size and brightness of superspirals weren't astonishing enough, there's another dimension where they push the cosmic envelope: star formation. In typical spiral galaxies like our Milky Way, star formation is a steady, patient process. The Milky Way gives birth to about 1 or 2 solar masses worth of stars per year. It's a calm, stable factory, churning out stars consistently but not excessively. But in superspirals, that gentle rhythm is replaced with an astronomical frenzy. These colossal galaxies are forming dozens, sometimes even hundreds of solar masses worth of stars every single year. That means dozens of stars like our Sun are igniting every year, and many of them are likely much larger, shorter-lived, and far more luminous. This isn't just high speed, it's cosmic overdrive, a star-forming rate that rivals or exceeds those seen in starburst galaxies, which are usually triggered by dramatic galactic collisions. But superspirals, curiously, often lack the visual chaos of a recent merger. So the question becomes, how are they forming stars so rapidly without descending into disarray? To answer that, we have to dive into the mechanics of star formation. Stars are born in vast clouds of gas and dust known as molecular clouds. Under the influence of gravity, pockets of gas within these clouds collapse, their temperatures rise, and nuclear fusion ignites. In the Milky Way, this process is widespread but relatively slow. Most molecular clouds take millions of years to birth clusters of stars, and much of the gas ends up being recycled or dispersed by stellar winds and supernovae. Superspirals, however, seem to exist in an entirely different mode. Their interstellar medium, the gas and dust that fills the space between stars, is abundant, dense, and highly organized. Observations suggest that these galaxies have enormous reservoirs of cold gas, especially hydrogen, the essential ingredient for star formation. This gas doesn't just sit passively in the disk, it flows, clumps, and ignites in a process that is both efficient and unrelenting. This creates a positive feedback loop. Gas flows into spiral arms, compresses due to the density wave structure, collapses into new stars, and those stars in turn release energy and winds that trigger further collapse in nearby clouds. It's a chain reaction that spreads across the entire galactic disk, creating waves of star birth that travel outward like ripples in a pond, except this pond is 500,000 light-years wide and blazing with stellar fire. In many galaxies, such high rates of star formation would be unsustainable. Supernovae would blast apart gas clouds. Radiation pressure would blow material out into intergalactic space. Yet somehow, superspirals maintain a balance between formation and destruction. The stellar nurseries continue to form stars without being ripped apart by the very forces they unleash. This implies a level of gravitational cohesion, likely due to massive amounts of dark matter, that holds the galaxy together while it operates at near maximum star-forming efficiency. What's even more fascinating is that this star formation is not confined to the central regions. In many high-luminosity galaxies, star birth is centralized near the core or in compact regions. But in superspirals, the entire disk is alive. Even the far reaches, regions hundreds of thousands of light-years from the core, show signs of ongoing stellar birth. This indicates that their gas supplies are not just deep but widespread, and their disks are somehow stable enough to support long-range propagation of star-forming activity. There's also evidence that metallicity gradients, the variation of elements heavier than hydrogen and helium, in these galaxies are surprisingly shallow. In most spirals, the outer regions are more metal-poor, reflecting less stellar processing over time. But in superspirals, the metal distribution is more even, suggesting that either the entire galaxy formed its stars more uniformly, or that internal mixing mechanisms, perhaps driven by bar structures or spiral arm dynamics, are redistributing materials more effectively than in smaller spirals. The presence of massive, young, blue stars gives these galaxies their vivid coloration in optical and ultraviolet wavelengths. These stars burn through their fuel quickly, some in just a few million years, and end their lives in cataclysmic supernovae, enriching the surrounding gas with heavy elements and seeding the next generation of stars. This cycle, creation, illumination, explosion, and enrichment, happens on a galactic scale, making the galaxy itself an engine of renewal that burns hot but somehow avoids burnout. Even more astonishing is how long-lasting this activity appears to be. Starburst galaxies, those experiencing short-lived periods of extreme star formation, typically burn through their gas in a few 100 million years. But superspirals appear to maintain their star-forming activity for billions of years. Their vast gas reserves, likely replenished through steady accretion from the cosmic web or minor mergers, allow them to sustain this cosmic frenzy without collapsing under the weight of their own luminosity. Some models suggest that superspirals may experience episodic starbursting, periods where gas inflow increases, igniting a fresh wave of star formation, followed by lulls where the galaxy stabilizes. But in either case, the average star formation rate remains orders of magnitude above what we see in the Milky Way. Over time, this leads to a cumulative effect, a buildup of an enormous stellar population that feeds back into the galaxy's gravitational potential, luminosity, and structure. And this isn't just an astronomical curiosity. The intense rate of star formation in superspirals has profound implications for understanding how galaxies build themselves. It shows that under the right conditions, spiral galaxies can form as many stars as the most active elliptical or irregular galaxies, all while maintaining coherent structure. It reveals that galaxy morphology, whether spiral, elliptical, or irregular, may not be strictly a consequence of mass or age, but of how a galaxy manages its gas, angular momentum, and internal feedback mechanisms. Observations in the ultraviolet and infrared spectrum further support this. UV light reveals the youngest, hottest stars, a clear tracer of recent star formation. Infrared light, meanwhile, shows the glow of warm dust heated by those same stars, offering another window into the intensity of these galactic furnaces. Both types of data reveal the same conclusion: these galaxies are forming stars everywhere, and they're doing it fast. It's also worth noting the rarity of this behavior. While many galaxies go through periods of elevated star formation, sustained high-rate star formation across hundreds of thousands of light-years is almost unheard of outside this superspiral class. They are not common. They are extreme outliers, blazing examples of what spiral galaxies can become under optimal, but incredibly rare, conditions. Superspirals, then, are not just bigger and brighter. They are fundamentally more productive. They are cosmic construction zones on a scale rarely witnessed, building the stellar framework of future galaxies, star clusters, and possibly planetary systems, all at once. And this frenzied activity is a vital part of what makes them so luminous, so massive, and so structurally surprising. They form stars not in quiet pockets, but in waves, storms, and sprawling fronts that light up their disks like fireworks. And somehow, against the odds, they keep spinning, forming, glowing, a perfect storm of gravity, gas, and light that refuses to fade. The revelation that such immense and luminous spiral galaxies could exist didn't come through a single moment of cosmic epiphany, but rather as a quiet anomaly buried within the vast oceans of astronomical data. The early 2000s saw a revolution in sky surveys, most notably the Sloan Digital Sky Survey (SDSS), a groundbreaking project that began mapping millions of celestial objects across the night sky with unprecedented precision and scale. It was within this colossal dataset, not from some distant satellite image, but from pattern recognition, that astronomers stumbled upon something truly bizarre: spiral galaxies that seemed too big, too bright, and too massive to make sense. The first major identification of these outliers came in 2015, when a team of astronomers led by Patrick Ogle at Caltech began digging deeper into high-luminosity galaxies cataloged by the SDSS. The team was particularly focused on galaxies that emitted more than 8 times the luminosity of the Milky Way, a threshold at which galaxies are generally expected to transition into elliptical or irregular shapes due to their violent formation histories. But buried among the ultraluminous galaxies, most of which were ellipticals, were several spirals. Spirals that were as luminous, as massive, and sometimes even more active than the rest. This didn't make sense at the time. The understanding among most astrophysicists was that as galaxies get more massive and luminous, their morphology changes. Spiral structure is delicate, prone to distortion or destruction in major galactic mergers, and unlikely to survive at those scales. And yet, here were these giants, pristine in their disks, with sweeping arms and central bulges intact, rotating like well-balanced gyroscopes in space. What's more, many of these candidate galaxies weren't newly imaged. They had been sitting in the SDSS database for years, overlooked because they didn't look unusual. Their appearance was deceptively ordinary, just like other spirals, until one noticed the scale bar. Then the enormity struck. These galaxies were hundreds of thousands of light-years across, forming stars at incredible rates, and emitting the light of 100 billion suns. The Caltech team, leveraging both SDSS data and photometric analysis from GALEX, Galaxy Evolution Explorer, and WISE, Wide Field Infrared Survey Explorer, began calculating their total luminosities, stellar masses, and estimated star formation rates. The numbers that emerged were staggering. These spiral galaxies had stellar masses up to 10 to the power of 12 solar masses and were emitting more than 100 billion solar luminosities, surpassing the brightness of many quasars. Yet they exhibited no signs of recent major mergers or violent disruptions. Their spiral arms were broad, structured, and sometimes even elegant. They were not transition cases, they were stable superstructures. To confirm these findings, follow-up observations were conducted using instruments like the Hubble Space Telescope, which helped resolve finer details in both near and far-field examples. Hubble's superior resolution was able to capture the delicate structure in some of these galaxies at distances of over 1 billion light-years. The images returned a resounding verdict. These were not distorted spirals caught mid-transition. These were fully formed, massive, and intact spiral galaxies that had either defied every galactic evolutionary model or were revealing a new, unknown track of galactic development. One of the earliest and most extreme cases to be formally documented was SDSS J094700.08 plus 254045.7, located about 1.2 billion light-years away. This galaxy became something of a poster child for the class. It was found to be more than 5 times the size of the Milky Way, had a stellar mass of over 1 trillion suns, and emitted more light than nearly any known spiral. Despite these extreme properties, its spiral structure was unmistakable. It didn't look like an elliptical pretending to be a spiral. It was a spiral, just on a different scale altogether. Another key player in these discoveries was the Galaxy Zoo project, a citizen science initiative that allowed volunteers to visually classify galaxies using SDSS data. While designed to crowdsource galaxy morphology across millions of samples, Galaxy Zoo inadvertently flagged several galaxies that, while appearing ordinary, consistently showed up in classifications as spirals despite having luminosities far above the spiral range. These citizen observations helped draw attention to these anomalous spirals and prompted deeper statistical reviews. As these galaxies came under more scrutiny, it became clear that they didn't represent just rare, isolated flukes. They hinted at an entirely uncharted territory in the galaxy population distribution. The initial catalog compiled by Ogle and his team included around 53 confirmed super-spiral galaxies, each with luminosities exceeding 8 times that of the Milky Way, many with star formation rates above 20 solar masses per year, and diameters well beyond 200,000 light-years. These were not just oddities. They were an emerging class. It also became clear that these galaxies were difficult to spot precisely because of their familiar morphology. Most galaxy surveys focus on redshift, brightness, or morphology individually, but superspirals challenge this separation. They occupy a strange corner of parameter space where mass, brightness, and structure intersect in a way not predicted by the classical Hubble sequence. They were hiding in plain sight, and it took a new way of thinking, not just looking, to notice them. In the years since the initial 2015 discovery paper, the list has grown slowly as new sky surveys and spectroscopic observations provide higher resolution data. Future instruments like the James Webb Space Telescope and the upcoming Vera Rubin Observatory are expected to uncover more of these massive spiral galaxies, especially at earlier cosmic epochs. What's exciting is that we may only be seeing the tip of the iceberg, the brightest and nearest examples. There could be hundreds or even thousands more, lurking deeper in the cosmos, hidden behind dust, distance, and classification biases. The discovery of superspirals is not just about adding a new name to the cosmic catalog. It's about realizing that the universe still holds surprises that challenge our deepest theoretical assumptions. It proves that even among millions of cataloged galaxies, new giants can be waiting in the data, defying the standard models with a quiet, radiant defiance. These discoveries weren't the result of new physics or exotic instruments, but of new perspectives, scientists and observers willing to revisit what was already seen, to question what had been assumed, and to reclassify the familiar when it no longer fit the rules. In this way, superspirals remind us not just of the size and power hidden in the universe, but of the importance of curiosity itself. One of the most perplexing and captivating features of superspirals is not just that they're enormous, or that they blaze with the light of a trillion suns, it's that they remain clean, ordered, and beautifully structured even while doing so. These galaxies aren't swirling maelstrom of chaos. They aren't torn or misshapen by recent collisions or twisted by gravitational tides. In fact, their structure often appears remarkably well-defined. Their spiral arms are coherent, their disks are flat, and their cores are centralized and bright, like classical textbook examples, just scaled up to galactic extremes. This is deeply counterintuitive. As galaxies grow in mass and size, they tend to become less organized, not more. Major mergers, one of the primary mechanisms of galaxy growth, tend to disrupt spiral structure, scrambling arms, puffing up the disk, and eventually transforming spirals into elliptical galaxies, rounded, featureless systems that have used up most of their gas and stopped forming stars. This is a cornerstone of galaxy evolution theory. Spirals are the youthful, active form. Ellipticals are the old, massive remnants. But superspirals exist in direct defiance of that expectation. So how can these titanic spirals retain their form despite possessing characteristics like extreme mass, high luminosity, and fast rotation that are usually linked with morphological breakdown? The answer seems to lie in a combination of factors, each delicately tuned in a way that allows these galaxies to maintain structural integrity under cosmic stress. One critical factor is angular momentum. Superspirals likely formed in environments or from processes that preserved, or even amplified, their original spin. A high degree of rotational momentum means that material in the galaxy settles into a stable disk, rather than collapsing inward or forming random, chaotic shapes. This momentum acts like a gyroscopic stabilizer, flattening the disk and spreading material across vast distances without the whole system falling apart. Another major factor is gravitational self-regulation. Superspirals are incredibly massive, and their mass is not confined to the stars we can see. The majority of it is thought to be dark matter, forming an immense and invisible halo that envelopes the entire galaxy. This dark matter halo acts as a gravitational backbone, preventing the disk from warping or tearing even as it spins at hundreds of kilometers per second. Think of it as scaffolding, unseen but critical, that lets the galaxy spin and shine without losing its shape. But it's not just about what holds them together. It's also about what they don't experience. The relatively clean appearance of superspirals suggests that many have had quiet merger histories, meaning they haven't undergone major galactic collisions in recent cosmic time. Unlike galaxies that have been battered by interactions, superspirals appear to have evolved in isolation, or at least without disruptive interactions. This isolation gives them time to grow, settle, and stabilize into their massive forms without being derailed by cosmic turbulence. This isolation may also explain their unusually cold, dense disks, conditions that promote calm, efficient star formation over violent bursts. While elliptical galaxies tend to be gas-poor and starved of new material, superspirals remain richly supplied, yet manage to convert that gas into stars in a manner that doesn't distort or warp the disk. It's an almost paradoxical balance, extreme activity housed within exceptional order. Computer simulations and models have also shed light on this phenomenon. Simulations like those from the Illustrious and Eagle projects show that under very specific conditions, such as early, smooth accretion of cold gas, a steady spin, and a calm cosmic neighborhood, galaxies can maintain disk structure while growing incredibly massive. But these conditions are rare, and that's likely why superspirals themselves are rare. They represent a narrow window of cosmic possibility. The right spin, the right environment, the right inflow of gas, and the absence of destructive collisions over billions of years. Interestingly, many superspirals also show symmetry on large scales. Their arms are often balanced, their cores centered, their disks nearly circular rather than elongated or skewed. This suggests an internal gravitational harmony, a balance between inflow and outflow, between centrifugal force and centripetal pull, between star formation and stellar death. They are not merely surviving at their massive scales, they're thriving in a state of rotational balance that allows for stability even in the midst of intense internal activity. Another clue may lie in barred spiral structures, features found in many superspirals. Bars are elongated regions of stars that stretch from the central bulge outward into the disk, and they're thought to help redistribute angular momentum and funnel gas inward, feeding both the central bulge and triggering new star formation. The presence of well-formed bars in some superspirals hints at dynamical maturity. These are galaxies that have evolved complex internal mechanisms to manage their mass and energy flows. And then there's the role of magnetic fields, which, while still poorly understood on galactic scales, are known to influence the motion of gas and the dynamics of star-forming regions. In a galaxy as massive as a superspiral, magnetic fields could play a role in shaping how gas moves through the disk, perhaps smoothing irregularities and helping maintain structural order over time. The order seen in superspirals also extends vertically. These galaxies have incredibly thin disks, even when they are hundreds of thousands of light-years across. This is particularly astonishing because maintaining thinness requires that the stars and gas move in relatively flat orbits, with minimal vertical motion. It's as if someone stretched a cosmic vinyl record to unimaginable size, but kept it razor-thin and perfectly spinning. This clean structure is not just aesthetically remarkable, it has scientific implications. It suggests that disk stability is not inherently limited by size or mass, as long as the right conditions are in place. It opens the door to rethinking galaxy morphology as a continuum, not a dichotomy between spirals and ellipticals. Perhaps, under specific evolutionary pathways, galaxies can remain spiral indefinitely, growing ever larger and brighter without losing their identity. And in a way, that's what makes them so profoundly unsettling and exciting. Superspirals don't just challenge the size scale of spirals. They challenge the concept of what a spiral galaxy can be. They hint that the elegant, spiral structure we see in the Milky Way isn't a fragile accident of a modest galaxy, but rather a robust configuration that can be scaled up to cosmic titans, if conditions are right. They are the cosmic equivalent of a supercomputer built from mechanical gears. Beautifully complex, impossibly large, yet still running smoothly. In them, we see not the fraying of structure at galactic limits, but the emergence of an unexpected order, an intelligent design, in a sense, crafted not by intent, but by physics, gravity, and time. In a universe filled with explosions, entropy, and decay, superspirals are harmonious exceptions. They are systems of controlled power, vast beauty, and architectural elegance. Their order is not just a cosmetic feature, it is a signal, a whisper from the cosmos that sometimes, in the most extreme conditions, nature doesn't unravel, it perfects. For decades, the dominant narrative in astronomy about how galaxies grow, evolve, and ultimately end up in the shapes we observe has been shaped by a combination of observations, simulations, and theoretical models. And all of them pointed toward one general rule: the bigger a galaxy becomes, the more likely it is to become an elliptical. That rule was so well accepted that for many astronomers, finding a massive galaxy still in spiral form was like discovering a skyscraper made entirely of glass in the middle of an earthquake zone, beautiful, improbable, and possibly unsustainable. But then came the superspirals, tearing a hole in that logic with their elegant arms and luminous disks. To understand why their existence is so revolutionary, we have to step back and revisit what galaxy evolution models have long taught us. In the early universe, galaxies started small. Little clumps of gas and dark matter condensed from the cosmic web, igniting stars and forming the first galaxies, irregular, turbulent, chaotic in shape. As time passed, these small galaxies merged, collided, and interacted with one another in a process known as hierarchical assembly. This model, backed by both observational evidence and simulations, suggests that galaxy mergers are the primary driver of growth in the universe. Little galaxies build up into medium-sized ones. Medium ones slam together and make giants. The more mass a galaxy accumulates, the more likely it has done so through major mergers, the astronomical equivalent of high-speed collisions. But here's the catch: major mergers are violent. When two galaxies of roughly equal mass collide, their internal structure is often destroyed. Spiral arms are shredded, disks are puffed up, and stars are thrown into random orbits. What emerges is usually not a bigger spiral, but a bulging, ellipsoidal mass, a classic elliptical galaxy. These are galaxies like Messier 87 or NGC 4889, giant, round, relatively featureless behemoths that no longer form many stars and glow faintly with the light of aging stellar populations. They are often considered the final evolutionary state of galaxies, massive, red, and dead. This pathway, from active, structured spiral to chaotic merger to passive elliptical, seemed universal. It was not just theory, it was reflected in the observed demographics of galaxies. When astronomers looked at the most massive galaxies in clusters, they were almost always ellipticals. Spirals, by contrast, dominated the lower mass population. There seemed to be a clear threshold of mass and luminosity beyond which spiral structure simply could not survive. That's why the discovery of superspirals was such a profound shock. Here were galaxies with stellar masses of 1 trillion suns, diameters up to 500,000 light-years, and star formation rates 10 to 100 times higher than the Milky Way, all of the hallmarks of a massive, evolved galaxy, and yet they were spirals. They had disks, arms, bars, and bulges. They had organization. They had rotational symmetry. They looked, in short, like they shouldn't exist. From the perspective of galaxy formation theory, these galaxies are anomalies that challenge the sequence of morphological transformation. They suggest that the rule, big galaxies become ellipticals, may be more of a trend than a law, and that alternative evolutionary paths may be possible. It raises a startling question: is there a whole family of galaxies that grow massive without major mergers, and if so, how? One hypothesis is that superspirals manage to grow quietly, through the steady accretion of gas and minor mergers, interactions with much smaller galaxies that don't disrupt the overall disk structure. If a galaxy can continue to feed on fresh cold gas from its surroundings, it can sustain star formation and build mass over billions of years without having to collide violently with its peers. But this pathway requires a stable cosmic environment, one where the galaxy isn't constantly threatened by large neighbors. And that kind of serenity, especially in the dense, crowded universe of galaxy clusters, is exceedingly rare. Another idea is that some of these superspirals might be late bloomers, galaxies that avoided early major mergers and only began their rapid growth phase relatively recently in cosmic terms. This would allow them to build up mass without having had their structure disrupted early on. But again, this scenario is rare, and it doesn't account for the sheer number of massive spiral galaxies now being discovered in different parts of the sky. Simulations have tried to model this behavior. In some high-resolution runs of the Illustrious and Eagle projects, computer simulations that track the evolution of galaxies across cosmic time, a handful of spiral galaxies reach very high masses without becoming ellipticals. But these are edge cases, and they usually require very specific initial conditions: high angular momentum, isolated formation environments, and continuous gas inflow. Even then, they often form bars or rings and eventually lose their symmetry. None of the models predicted the existence of so many clean, massive spiral galaxies, not until the observations forced theorists to look again. And there's another layer of mystery. These galaxies aren't just massive, they're active. They're forming stars at a breakneck pace, lighting up the sky with their youthful blue hues. Yet, according to traditional models, massive galaxies should have long since run out of gas. Star formation uses up gas, and feedback from supernovae and central black holes is supposed to heat or blow away what remains. But superspirals still have gas, and lots of it. That implies that either they've avoided the feedback processes that shut down star formation in other giants, or they've been replenished somehow, maybe through cold streams or galactic fountains that re-inject gas into the disk. Either way, it's a direct violation of what we thought we knew about how galaxies quench and age. Even the internal composition of these galaxies defies expectations. Some superspirals show evidence of young stellar populations and relatively uniform metallicity, suggesting that not only are they still forming stars, but they've been doing so consistently, across their disks, for billions of years. That longevity of star formation, combined with massive scale and preserved structure, is something models have yet to convincingly explain. What does all this mean for our understanding of galaxy evolution? In a word, recalibration. The discovery of superspirals forces astronomers to reconsider what's possible in the universe. It shows that there's not just one path to galactic maturity. There might be multiple evolutionary tracks, some violent and chaotic, others smooth and orderly, each producing different outcomes depending on a galaxy's environment, spin, gas supply, and interaction history. In this way, superspirals are not just scientific curiosities. They are cosmic counterarguments, living proof that the universe isn't as deterministic as we thought. Their presence challenges us to widen our frameworks, revisit our simulations, and re-express our models in terms not of what should happen, but of what can. It's an exhilarating reminder that the universe still has the capacity to surprise us. Just when we think we've built a complete map of the cosmos, something like a superspiral appears, pointing to a road we didn't even know existed, a spiral path winding through a terrain we once thought was flat. Despite their brilliance, their sheer size, and their star-forming frenzy, superspirals remain astonishingly rare. In a universe teeming with hundreds of billions of galaxies, only a few dozen confirmed examples of superspirals have been catalogued to date. And that number, as of now, doesn't even break into the hundreds. These cosmic giants stand alone, not just physically, but statistically. The question that naturally follows is, why? Why are they so rare, especially when other massive galaxy types, like ellipticals, are relatively common? To understand this rarity, we need to consider what it takes to create and sustain a superspiral galaxy. These aren't just larger versions of normal spirals. They are exquisite balancing acts, pushing the boundaries of galactic physics without collapsing under their own complexity. Their existence depends on a combination of extreme yet finely tuned conditions, each of which is rare on its own. Together? Nearly astronomical. First and foremost is the issue of angular momentum. For a spiral galaxy to exist, let alone a superspiral, its material must be rotating with enough speed and stability to flatten into a disk rather than condense into a spherical blob. Angular momentum prevents the collapse of gas and stars into the center, and allows material to settle into a rotating, structured form. But as galaxies grow more massive, their tendency is to lose this rotational symmetry. Frequent mergers, accretion of material from various directions, and gravitational torques can disrupt or cancel out the rotational motion needed to maintain a disk. Only galaxies that manage to preserve and amplify their angular momentum during growth can become, or remain, spirals. Then there's the issue of massive dark matter halos. Superspirals aren't just big in terms of visible stars. They're embedded within enormous halos of dark matter, the invisible glue that provides the gravitational stability needed to hold their massive rotating disks together. But such halos are statistically uncommon. Most massive halos either end up hosting giant ellipticals or become gravitationally overwhelmed by their surroundings in dense galaxy clusters. Superspirals require dark matter halos that are not only massive but also relatively isolated and undisturbed, giving them room to spin up and form stars without being stripped or harassed by neighboring galaxies. The next ingredient is cold gas, specifically, a sustained supply of cold hydrogen gas to fuel intense and long-term star formation. In most massive galaxies, this gas is either exhausted quickly during starburst phases or heated and blown away by feedback from active galactic nuclei, AGN, or supernovae. Once that gas is gone, star formation slows, and the galaxy transitions into a more passive state. Superspirals, however, must either avoid that quenching process or continually replenish their gas through inflows from the cosmic web or minor mergers with gas-rich dwarf galaxies. Maintaining such a high inflow rate over billions of years, without disrupting the disk, is incredibly rare. The environment plays a pivotal role as well. Superspirals are most often found in low to moderate density cosmic environments, the so-called cosmic suburbs. Too close to galaxy clusters, and the gravitational tides and frequent interactions destroy disks. Too isolated, and the galaxy may not accrete enough material to grow to superspiral status. They need just enough neighbors to feed on, without becoming engulfed in chaos. It's a narrow window, and few galaxies find themselves in the right place at the right time with the right ingredients. But there's more. The formation of a superspiral may also be tightly constrained by timing. Galaxies that grew up too early in the universe's history likely experienced violent mergers when the universe was more crowded and chaotic. Those that grew too late may not have had enough time to accumulate the necessary mass and structure. Superspirals may represent a very specific temporal evolutionary window, a kind of cosmic adolescence that happens around a few billion years ago, when conditions were just right for this type of growth to occur without disruption. This combination of strict requirements, angular momentum preservation, massive dark matter halos, ongoing gas inflow, minimal disruptive interactions, optimal environment, and precise cosmic timing, forms what might be called a galactic Goldilocks zone. Everything has to be just right. If even one variable shifts, the galaxy either never forms, gets torn apart, burns out too fast, or becomes something else entirely. It's like baking a cake in zero gravity with ingredients floating in from random directions, and yet somehow, the recipe holds, and the result is majestic. There's also a significant observational bias to consider. Superspirals are often incredibly distant, with many discovered more than 1 billion light-years away. That means we are often looking at them as they were long ago. Because of their brightness, they do stand out in wide-field sky surveys, but their great distance makes detailed analysis difficult. It's possible that many more superspirals exist, or existed, beyond our current detection limits, and we simply haven't seen them because they're either too far away or camouflaged in massive data sets awaiting deeper inspection. Additionally, many galaxies that could have become superspirals might have followed alternate fates. A minor collision here, a misaligned gas inflow there, and the path veers off course. Instead of forming a pristine disk, the galaxy becomes lopsided, deformed, or converts into a more chaotic structure. Even galaxies that momentarily resemble superspirals may transition away from that phase relatively quickly, burning out their gas or undergoing a merger that ends the spiral structure. This raises the possibility that superspirals are not just rare, they may be short-lived, in cosmological terms. Perhaps they're transitional giants, burning brightly for a few billion years before fading or transforming into something less recognizable. And let's not forget the role of human classification error. Before the term superspiral was even coined, astronomers had already catalogued hundreds of these galaxies in surveys like SDSS, WISE, and Galactic, but didn't realize what they were. They were marked down as spirals, yes, but their extreme luminosities and sizes were not always flagged. It wasn't until the data was reanalyzed with new criteria, looking at total brightness, star formation rates, and structural size together, that the uniqueness of these systems was revealed. It's entirely likely that many more superspirals remain hiding in plain sight, miscategorized or simply not yet examined in detail. Even if we were to discover hundreds more, superspirals would still represent a minute fraction of all known galaxies. Most galaxies are small dwarfs. A small minority are giant ellipticals. Spirals like the Milky Way form a significant portion of the observable cosmos, but superspirals? They are the top 0.01%, the Olympians of the galaxy world. In a universe where entropy and chaos dominate, their rarity is a testament to just how hard it is to stay balanced, structured, and brilliant at once. In the end, their rarity is what makes them precious. It is what gives them the power to challenge assumptions and upend models. If superspirals were everywhere, they would merely be the norm. But because they are so uncommon, they become a window into the extreme limits of galaxy formation, teaching us not only what is possible, but what is improbable yet real. They are rare because they must be. The universe doesn't easily make things that are enormous, elegant, and enduring all at once. And when it does, we call them by a name that hints at myth and magnitude alike, superspirals. One of the most jaw-dropping characteristics of superspirals, something that truly stretches our understanding of galactic physics, is how fast they spin. Not just fast in the everyday sense, not even just fast in astronomical terms, but so fast that in some cases, the outer edges of these galaxies rotate at velocities approaching relativistic thresholds, meaning they begin to inch closer and closer to a significant fraction of the speed of light. It's a cosmic ballet played at breakneck tempo, and somehow, against all expectation, the dancers never stumble. These galaxies don't tear themselves apart. They hold together, neatly and elegantly, with spiral arms spinning in almost supernatural cohesion. To understand how astonishing this is, we need to take a step back and look at what it means for a galaxy to rotate. Spiral galaxies like the Milky Way are not static structures. Every star, gas cloud, and dark matter particle is orbiting the center of mass, rotating in a flattened disk around a central bulge. Our own Milky Way spins at an impressive clip, at the Sun's location, around 27,000 light-years from the galactic center. We're orbiting at about 220 kilometers per second, or nearly 500,000 miles per hour. That's fast enough to circle Earth 20 times in a minute. But superspirals laugh in the face of that number. In several observed superspirals, especially those pushing the upper end of the mass and size distribution, rotation velocities at the outer edge can exceed 350 to 400 kilometers per second. Some even approach 500 kilometers per second, speeds that push the very limits of what a rotating disk galaxy should be able to do without flying apart. These speeds are not just theoretical calculations. They're measured using the Doppler shift of spectral lines, especially hydrogen's famous 21 centimeters emission line, which allows astronomers to precisely track the velocity of gas orbiting in the disk. Let's put this into perspective. At a rotation speed of 500 kilometers per second, an object could travel from the Earth to the Moon in about 13 minutes. If you had a spaceship moving at that speed, you could fly from one side of our solar system to the other in mere days. And in these galaxies, it's not just one object, it's billions of stars and clouds of interstellar gas, all moving at these tremendous velocities, across disks that span hundreds of thousands of light-years. What's truly mind-bending is that the disks don't tear themselves apart. You might expect such rotational speeds to create extreme centrifugal forces that would rip stars and gas out of the disk and fling them into intergalactic space. But that doesn't happen. Instead, the disk remains intact, flat, and coherent. Why? The answer, once again, lies in gravity, and especially dark matter. The stars and gas we can see in a galaxy only make up a small fraction of its total mass. The lion's share is hidden in a vast halo of invisible dark matter, extending well beyond the visible edges of the disk. This dark matter acts like a gravitational anchor. As the outer parts of the galaxy try to fly outward due to rotation, the dark matter pulls them back in, maintaining the structure's cohesion. It's like an invisible scaffolding holding up a rotating city built on stilts. In fact, the rotational speed of galaxies was one of the original clues that led scientists to propose the existence of dark matter in the first place. In the 1970s, pioneering astronomer Vera Rubin observed that the outer stars and galaxies were rotating much faster than they should have been, based on the visible mass. Instead of slowing down with distance from the center, as Newtonian physics would predict, the stars maintained constant, or even increasing speeds. The only explanation was that there was much more mass present than we could see. Something invisible, massive, and pervasive was providing the gravitational glue. And in superspirals, this effect is turned up to the maximum. Their rotation curves, graphs that plot rotational velocity against distance from the galactic center, are some of the flattest and highest ever recorded. This means that even at distances of 100,000 to 200,000 light-years from the center, stars and gas are still whipping around at speeds that suggest enormous gravitational influence. The implication is that these galaxies are embedded in dark matter halos of staggering proportions, halos that could be 10 or even 20 times more massive than the visible part of the galaxy. Another intriguing implication is galactic stability. Fast rotation isn't just a sign of strength, it also helps regulate the structure of the galaxy. Rotational motion counteracts gravitational collapse, allowing the disk to stay thin and ordered. In most galaxies, increased mass often leads to instability, vertical thickening, or bar-driven chaos. But in superspirals, rotation seems to be the key to preserving spiral structure even in the face of massive scale. The disk remains thin, The spiral arms stretch elegantly outward, and the overall shape resists distortion. Some astronomers suspect that this rotational stability may even be self-reinforcing. The faster the galaxy spins, the more angular momentum it accumulates. The more angular momentum it has, the more evenly material is distributed across the disk. The more uniform the disk, the more stable its gravitational profile. It's a feedback loop of balance, delicately tuned over billions of years. But there's an additional, more speculative idea. Perhaps these superspirals never experienced major mergers, which are notorious for destroying rotational coherence. Instead, their growth may have been driven by smooth gas accretion and minor mergers that add mass without disrupting spin. This would allow them to maintain, and even enhance, their rotation as they grew. They didn't explode into greatness. They spun into it. There's also the potential role of magnetic fields and dynamical feedback. In such extreme environments, it's possible that rotational speed and magnetic confinement interact in complex ways, helping to stabilize gas clouds and regulate star formation. This might explain why many superspirals are so efficient at turning gas into stars without triggering the kind of feedback that quenches or destabilizes the disk. And while none of these galaxies rotate at speeds truly relativistic, in the strict physics sense, meaning close enough to the speed of light that Einstein's theories must come into play, the term is not just hyperbole. At these velocities, especially in the inner regions of the galaxy where speeds can approach 600 to 700 km/s, time dilation and relativistic mass effects do start to become non-negligible, especially when measuring the behavior of high-energy particles or interpreting the motion of gas near supermassive black holes in the center. Speaking of central black holes, some of these fast-rotating galaxies are suspected to host supermassive black holes that may be influencing galactic rotation in subtle but measurable ways. The central bulges in some superspirals contain enough mass to rival entire small galaxies, and their influence on surrounding star orbits, especially in the inner tens of thousands of light-years, may be critical in regulating the overall rotation profile. In sum, the rapid rotation of superspirals isn't just a curious side effect of their size, it's a foundational aspect of their survival. Without it, their disks would collapse, their structures would degrade, and their orderly spirals would blur into chaos. Instead, their incredible rotational velocity is a signal, a pulse from the deep universe telling us that under the right conditions, speed is order. They are not spinning out of control. They are spinning into perfection. And in doing so, they show us that motion and stability are not opposites, but companions. In a cosmos where stillness often means death, these galaxies thrive by racing forward, defying entropy not through stillness, but through spin. In the high-speed, high-mass, high-energy world of superspiral galaxies, the question isn't just how they shine so bright or grow so big, it's how they hold themselves together. These galaxies are spinning at hundreds of kilometers per second, forming stars at rates that should exhaust their gas, and stretching across 500,000 light-years or more. By all rights, they should tear themselves apart. And yet they don't. Instead, they maintain their elegant spiral arms, their flat disks, and their internal coherence across staggering scales. How is that possible? The answer, overwhelmingly, points to one of the most mysterious and dominant components of the universe: dark matter. Dark matter is invisible. It doesn't emit light, reflect it, or interact with electromagnetic forces in any way we can detect directly. But we know it's there, not because we can see it, but because we can see what it does. It exerts gravity. It warps the motion of stars and galaxies. And it holds together structures that, by all appearances, should be flung apart by their own momentum. In superspiral galaxies, dark matter isn't just important. It's essential. Without it, the entire structure of a superspiral would disintegrate. The visible mass, stars, gas, dust, simply doesn't provide enough gravity to keep such a massive, fast-spinning disk intact. If the galaxy were made only of the matter we can see, its outer arms would be flung into space like debris from a centrifuge. But that doesn't happen. Instead, the arms remain anchored. The stars stay in orbit. The galaxy survives, and thrives. This is where the concept of a dark matter halo comes in. Every spiral galaxy is believed to be embedded in a vast, roughly spherical cloud of dark matter that extends far beyond the visible edge of the disk. For a galaxy like the Milky Way, this halo is already massive, possibly extending 300,000 light-years out, containing 5 to 10 times more mass than the visible stars. But for superspirals, the halos must be even larger. The dark matter halo of a superspiral could span over 1 million light-years, with a mass potentially exceeding 10 trillion solar masses. That's an order of magnitude beyond what's observed in regular galaxies. This halo acts as an invisible scaffold. It supplies the gravity needed to counterbalance centrifugal forces generated by the galaxy's rotation. It's like a gravitational net that keeps everything tethered: the stars, the gas, the spiral arms, even the interstellar dust, all locked in orbital harmony. The evidence for this comes from detailed rotation curves, which plot the orbital speed of stars and gas as a function of distance from the center. In a galaxy governed only by visible mass, these speeds should drop off with distance, like planets in the solar system. But in both ordinary spirals and superspirals, the speeds remain flat, or even slightly rising, far beyond the point where visible matter can account for the gravity. This discrepancy is the gravitational fingerprint of dark matter, and in superspirals, it's amplified. But the dark matter halo doesn't just hold the galaxy together gravitationally. It may also play a role in how the disk forms and evolves. Simulations suggest that the shape and angular momentum of the dark matter halo can influence the formation of the visible galaxy. A flattened, spinning halo can help form a large disk structure, guiding the collapse of gas and stars into a spiral rather than a spheroid. Moreover, the mass distribution of the halo can influence the stability of spiral arms, bars, and rings, preventing them from dissolving under the stress of internal dynamics. In superspirals, the halo might also protect the galaxy from external threats. In dense galactic environments, interactions and tidal forces from neighboring galaxies can distort or destroy spiral structure. But a massive dark matter halo can act like a gravitational shield, absorbing much of the stress and protecting the fragile disk inside. This could be why many superspirals are still so pristine. Their halos act like shock absorbers in a violent cosmic sea. There's also growing evidence that dark matter may affect the cooling and accretion of gas. In the early universe, as galaxies formed, the inflow of cold gas into dark matter halos was essential for fueling star formation. If the halo is massive enough and has the right thermal properties, it can act as a reservoir, capturing gas and slowly funneling it toward the disk. This process could explain how superspirals continue forming stars over billions of years without running out of fuel. The halo serves not just as a structural anchor, but as a cosmic supply chain, feeding the galaxy from the outside in. The interplay between visible matter and dark matter is especially critical at the edges of these galaxies. In superspirals, the outer disk can extend hundreds of thousands of light-years, well into the region dominated by dark matter. And yet, these outer stars rotate at speeds similar to the inner ones. This means that the dark matter is doing the heavy lifting, providing the vast majority of gravitational force in the outer regions. The stars and gas at these edges are essentially orbiting within a dark matter ocean, invisible but profound. One of the more exotic ideas is that dark matter itself may be dynamic, not just a passive gravitational presence but a contributor to galaxy behavior in more active ways. Some theories propose that dark matter might have interactions, beyond gravity, that affect how it clumps or moves. If that's true, then the shape and behavior of a superspiral's halo could have unique features not yet fully understood. Some simulations even suggest that rotating dark matter halos could transfer angular momentum to the disk, amplifying its spin over time. This could be another piece of the puzzle in explaining how superspirals maintain such high rotation rates. And then there's the dark matter's potential influence on galactic stability. One of the biggest mysteries in spiral galaxies is why their arms persist for billions of years. According to early models, spiral arms should wind up and fade over time, yet they don't. In superspirals, this longevity is even more puzzling. But simulations show that density waves, supported by the gravitational potential of the dark matter halo, can help sustain spiral structure over cosmological timescales. It's like the halo provides the stage, and the stars perform the dance. There's still so much we don't know. Dark matter has never been detected directly. Its properties remain speculative, constrained only by the effects we can observe. But in superspirals, its presence is more than a mathematical placeholder, it's a necessary foundation. Without it, the most majestic structures in the universe would simply fly apart. In a way, dark matter is the silent architect of these giants. It builds nothing we can see, but it holds everything we can. It creates no light, but it shapes the luminous spiral arms that stretch across intergalactic space. In superspirals, we see its fingerprint on the grandest scale, not as a mystery to be feared, but as a framework to be admired. They spin, they shine, they thrive, not in spite of darkness, but because of it. When astronomers first laid eyes on superspirals, their sheer size and brilliance suggested ancient, evolved galaxies. After all, something so massive and structured, something that defies the traditional fate of becoming an elliptical, must surely be old. It must have taken countless billions of years to build a structure hundreds of thousands of light years wide, to form trillions of stars, to stabilize into a flattened, spinning disk. But as scientists peered deeper, analyzed more carefully, and compared observations across multiple wavelengths, a surprise emerged. Many of these giants are unexpectedly youthful. Youth in galactic terms doesn't mean just born. Of course. It means they're still actively forming stars, often at extraordinary rates, and their stellar populations contain a high fraction of young, hot, blue stars, the cosmic equivalents of newborns. These O and B-type stars, blazing in ultraviolet light, don't live long, maybe only a few million years. Their presence indicates recent and ongoing star formation. And for superspirals, the amount of UV light radiating from their disks is off the charts. This is not what you'd expect from ultramassive galaxies. Most galaxies that reach the upper tiers of mass, into the hundreds of billions or trillions of solar masses, quench their star formation relatively early in cosmic history. As they accumulate gas and stars, they grow hot and turbulent. Their central black holes flare up into quasars or active galactic nuclei, ejecting energy and gas into space. Their interstellar medium becomes heated or stripped, and new stars cease to form. These galaxies become red and dead, filled with old, cool stars and very little new stellar activity. But superspirals break this trend. Despite their immense mass, many of them are still blue. Still star-forming. Still surrounded by cool gas. They act like youthful galaxies trapped in the bodies of elders. Take SDSSJ 094700.08 plus 254045.7, for example, one of the most luminous and massive superspirals ever observed. It's forming stars at a rate between 20 and 60 solar masses per year, compared to the Milky Way's modest 1 to 2. This is not the behavior of an old, passive galaxy, it's a stellar nursery on steroids. Its light is not dominated by ancient red stars, but by massive, hot, young stars that live fast and die violently. This pattern repeats across the class. Superspirals often show ultraviolet excesses in their spectra, signaling widespread, intense star formation across vast stretches of their disks. Infrared data from the WISE and Spitzer telescopes also reveal warm dust, heated by massive young stars. In many of these galaxies, the dust is concentrated not just in the core, but across spiral arms that stretch out for hundreds of thousands of light years. These are not silent giants. They are celestial forges, still hammering new stars into existence. So why are they still young? Why haven't they burned through their gas? Why haven't feedback processes, like supernovae and AGN outflows, shut down their star formation? One possible answer is that superspirals exist in a rare evolutionary sweet spot, where everything aligns perfectly to allow sustained youthfulness. Their enormous dark matter halos provide not just structural stability, but also long-term gravitational influence that can funnel fresh gas into the disk from the intergalactic medium. Rather than blowing their fuel all at once in a massive starburst, they may regulate star formation through a balance of inflow, angular momentum, and feedback, keeping the fire burning without consuming all the wood. Another possibility is that these galaxies are late bloomers, Perhaps they formed relatively recently in cosmic history, avoiding the chaotic, merger-heavy early universe that turned so many other massive galaxies into ellipticals. By forming more gradually, they may have built up their mass while maintaining disk-like structure and accumulating gas from smoother, colder flows. Some superspirals may have experienced minor mergers that added gas without disrupting the disk. These gentle collisions could bring in new material to fuel star formation while preserving the rotation and structure of the host. In fact, the presence of extended star-forming rings and asymmetrical spiral arms in some superspirals hints at past interactions, not violent enough to destroy them, but enough to stir up their gas and ignite waves of stellar birth. There's also the possibility that internal bar dynamics play a role in regulating their youth. In many spiral galaxies, a central bar structure acts like a conveyor belt, channeling gas from the outer disk inward. This can trigger central starbursts and feed a central black hole, but in superspirals, the bar may be long-lived and stable, providing a steady stream of gas to the inner regions without destabilizing the overall disk. This keeps the galaxy actively forming stars without entering a phase of runaway feedback that would shut the process down. And then there's the role of gas recycling. When stars explode as supernovae, they release gas back into the interstellar medium. In many galaxies, this gas is lost to space, but in the deep gravitational well of a superspiral, it may fall back into the disk, cool, and form stars again. It's a closed-loop ecosystem, where stellar death feeds stellar birth, and the cycle continues longer than in less massive galaxies. Astronomers are now using tools like the Hubble Space Telescope and the James Webb Space Telescope to probe the ages of stellar populations in these giants. What they're finding is a mosaic of ages. Old stars near the core, yes, but surprisingly large populations of young stars in the outer arms and across the disk. This suggests ongoing growth, not just in terms of mass, but in literal galactic youth. In some cases, it's possible that half the visible stars in a superspiral were born in the last 2 billion years, incredibly recent by cosmic standards. This youthfulness challenges traditional galaxy evolution models. According to many simulations, by the time a galaxy reaches a certain mass, quenching is inevitable. But superspirals don't seem to have read the script. They continue forming stars at a furious pace, radiating youthful energy across vast expanses. They are the Peter Pans of the universe, refusing to grow old, even as they grow massive. It also raises tantalizing questions about their future. How long can they sustain this star formation? Will they eventually quench and become giant lenticulars or ellipticals? Or are they capable of remaining active far longer than current models predict? Do they represent a final phase of orderly star formation before galactic transformation? Or are they stable endpoints, galaxies that will resist aging and burning out for billions of years to come? For now, one thing is clear: superspirals are alive. They're not fading into darkness. They're blazing with the birth of new stars. In a universe filled with relics and ruins, these galaxies are still under construction, still surging with youthful energy. They are massive, ancient in form, but young at heart. And in their luminous disks, we see a defiance not just of size or structure, but of cosmic aging itself. The youthfulness and star-forming vitality of superspiral galaxies leads us inevitably to one of the most crucial and puzzling questions in all of galactic astrophysics. How do they keep going? Galaxies don't produce stars out of nothing. Stars are born from cold gas, mostly hydrogen, that collapses under gravity into dense molecular clouds. These clouds fragment and ignite into blazing nuclear furnaces, stars. But the thing is, gas is a finite resource. Use it too fast, and a galaxy goes quiet. Deplete the reserves, and the star formation shuts down. In most massive galaxies, this happens early. But in superspirals? The engines keep roaring. To fuel the astonishing rates of star formation we observe in superspirals, tens to hundreds of solar masses per year, a galaxy would need a steady, abundant supply of gas over cosmic timescales. That's billions of years of continuous replenishment, across regions stretching hundreds of thousands of light years. And yet, unlike starburst galaxies that briefly flare and then fade, superspirals appear to sustain their activity over long periods. The big question is, how? The first answer lies in their initial gas reservoirs. Superspirals are gas-rich by nature. When they formed, they likely had access to tremendous quantities of cold hydrogen, either through direct accretion from the early cosmic web or from the collapse of enormous protogalactic clouds. Their dark matter halos, being massive and gravitationally deep, could gather and hold on to this gas without it being stripped away by other galaxies or cosmic radiation. Essentially, they started life with full tanks. But even with a generous starting supply, that gas would eventually run low, especially at the star formation rates we observe. So the next piece of the puzzle is replenishment. Observations and simulations suggest that many superspirals continue to draw in cold gas from their cosmic environment, a process known as cold flow accretion. Unlike violent mergers or hot gas halos, cold flows involve relatively smooth, filamentary streams of cool hydrogen from the intergalactic medium, funneled along the tendrils of the cosmic web directly into the galaxy's disk. This process is especially effective in massive dark matter halos, which can act as gravitational catch basins, pulling gas inward. These inflows may happen quietly, without disrupting the galactic structure, a gentle infusion rather than a turbulent upheaval. In this way, superspirals can continue drawing in gas for billions of years, feeding their star-forming regions and maintaining their brilliance. Another mechanism for sustaining star formation is recycling. When stars die, especially in the form of supernovae, they don't simply vanish. They return enriched material, metals, dust, and hydrogen, back into the interstellar medium. In lower mass galaxies, much of this gas is ejected into space and lost forever. But in superspirals, the gravity is so immense that even violent supernova explosions can't escape. The gas falls back into the galaxy, cools, and becomes part of the raw material for the next generation of stars. This process creates a closed feedback loop. Star formation leads to stellar death, which leads to more gas, which leads to more stars. The cycle continues. The sheer scale of superspirals allows this loop to function more efficiently, and for much longer than in smaller systems. But perhaps most surprisingly, these galaxies seem to avoid the catastrophic quenching seen in other massive galaxies. In typical massive systems, central black holes grow quickly and begin to emit intense energy in the form of AGN feedback, radiation, jets, and winds that heat the surrounding gas or blow it out of the galaxy entirely. This process is thought to be one of the primary reasons most large galaxies become elliptical and stop forming stars. But in superspirals, something different seems to be happening. Either their central black holes are relatively quiet, or the energy they emit is channeled or distributed in such a way that it doesn't shut down star formation. It's possible that feedback mechanisms are finely tuned, allowing gas to remain cool and dense in the disk while still regulating black hole growth. Or perhaps the black holes themselves are unusually well behaved, not triggering the kind of violent outflows that sterilize other galaxies. In either case, the result is that gas remains available and usable, even in the face of potential quenching forces. Moreover, some studies suggest that bar structures within the superspirals may be playing a critical role in redistributing gas. Bars can act like conveyor belts, channeling gas from the outer disk inward toward the central regions. This not only fuels starbursts in the core, but also stabilizes the disk by preventing the gas from becoming clumpy or inefficient. The bars essentially optimize the use of gas, moving it to where it can be most effectively turned into stars. Then there's the phenomenon of extended gas disks. In many superspirals, neutral hydrogen, HI, gas has been detected far beyond the visible edges of the stellar disk, in some cases out to 300,000 light-years or more. These gas halos are vast, diffuse, and cold, exactly the kind of raw material needed for future star formation. As the inner disk consumes gas, the galaxy can tap into these reservoirs, gradually drawing material inward through gravitational torques, viscosity, or tidal effects. What's more, these outer regions may serve as buffer zones, absorbing minor interactions or inflows from small satellite galaxies without disturbing the more organized inner disk. In this way, superspirals can quietly cannibalize their surroundings, feeding on cosmic leftovers without engaging in destructive mergers. These low-impact interactions provide fresh material without compromising structural stability, the best of both worlds. New observations with instruments like ALMA, ATACM, a large millimeter/submillimeter array, and the VLA, Very Large Array, are starting to map the cold molecular gas in these giants in exquisite detail. What they're finding is astonishing: rich, dense clouds of molecular hydrogen and CO, carbon monoxide, that extend across spiral arms, often in regions of intense UV radiation and young stars. These molecular nurseries are the heart of ongoing star formation, and their sheer abundance in superspirals suggests that the supply chain is far from empty. And now, with the James Webb Space Telescope peering into these galaxies in infrared, scientists are beginning to detect dust-shrouded star-forming regions that were previously invisible. These regions may contain hidden gas reservoirs, protected from UV feedback, quietly churning out stars and replenishing the galaxy from within. So, while the Milky Way carefully rations its star formation, superspirals seem to be running an interstellar feast, with deep pantries, efficient recycling, and cosmic supply lines extending across the universe. They are not reckless. They are sustained. In a sense, these galaxies have mastered the art of long-term fuel management. They are factories of light, powered by gas flows that remain active and efficient long after other giants have gone silent. They do not burn out quickly. They endure, consuming slowly, spinning steadily, and lighting up the cosmos with the fire of constant creation. In their vast arms, the story of matter becomes a symphony of transformation: hydrogen into helium, clouds into stars, light into life. And beneath it all, a supply of gas that flows, recycles, and returns, an eternal current feeding the fire at the heart of these galactic behemoths. One of the most astonishing mysteries surrounding superspirals is not just that they exist, but how they exist in such a pristine, organized, spiral form despite their immense size and luminosity. According to conventional wisdom in galactic evolution, when galaxies grow to enormous scales, especially those comparable to or surpassing the mass and size of superspirals, they often achieve that mass through mergers. Galaxies collide, coalesce, and combine into more massive structures. But there's a catch. Mergers usually destroy spiral structure. Colliding galaxies typically lose their neat, ordered disks. Their spiral arms get torn apart by gravitational forces, their stars are flung into random orbits, and the beautiful rotating symmetry is shattered. What emerges from these encounters is usually an elliptical galaxy, a puffball of stars without any coherent rotation. So the question naturally arises: how did superspirals become so massive without becoming ellipticals? Did they grow through mergers? And if so, how did they preserve their spiral form? This question goes right to the heart of galaxy formation theory and challenges our understanding of how galaxies evolve over billions of years. One possible answer lies in the distinction between major and minor mergers. A major merger involves two galaxies of roughly equal mass colliding. These events are typically catastrophic, leading to massive disruption and ultimately destroying any disk-like structure. But minor mergers, where a large galaxy consumes much smaller ones, are far more common and much less violent. In many cases, a spiral galaxy can merge with smaller satellites without significantly disturbing its disk. Superspirals may be the product of hundreds or thousands of minor mergers, gradually accreting mass over time like a snowball rolling down a hill. Each small galaxy adds stars, gas, and dark matter, helping the central galaxy grow in size and mass. But because the incoming satellites are relatively tiny, they don't destroy the overall structure. This kind of gradual, inside-out growth could allow the galaxy to grow enormous while still retaining its spiral shape. Another theory proposes that cold gas accretion, rather than mergers, may have played a more dominant role in their growth. In this scenario, the galaxy doesn't need to collide with others to grow. Instead, it steadily draws in cold gas from the intergalactic medium, fueling star formation and allowing it to expand organically. This process is much quieter and smoother than mergers and helps preserve the delicate rotational balance needed for a spiral structure. But there's also compelling evidence that some superspirals did experience significant mergers, and yet somehow managed to rebuild or retain their disk afterward. This idea may seem counterintuitive, but recent simulations show that under specific conditions, even a major merger can lead to the reformation of a spiral galaxy. Here's how it might work. If the two colliding galaxies are gas-rich, and if the interaction doesn't destroy all of the angular momentum, then after the initial chaos of the merger, the gas can settle back into a disk. Over time, new stars form within that disk, re-establishing spiral arms and creating a new spiral galaxy from the wreckage of the old. This process can take several 100 million years to a few billion years, but it's not just a theoretical possibility. It's been observed in simulations and even hinted at in certain real-world galaxies. Superspirals, with their immense mass and gas reservoirs, may have undergone such disk reformation after one or more mergers. In fact, some superspirals show asymmetrical arms, warps in their disks, or signs of tidal interactions, subtle clues that hint at a merger-rich past. These scars don't break the spiral structure but suggest it was challenged and rebuilt. There's also the notion of gas-dominated mergers. If two galaxies with unusually high gas content collide, the interaction may not destroy the disk, but rather compress the gas and trigger massive star formation, enhancing the spiral structure rather than erasing it. This is especially true if the collision happens in a relatively face-on or aligned orientation, minimizing the impact on angular momentum. In such cases, rather than collapsing into a spheroid, the result may be a supercharged spiral, exactly what we observe in some superspirals. Another possibility is that superspirals are hybrid structures, products of both smooth accretion and selective mergers. They may have experienced quiet growth through gas inflow for billions of years, occasionally punctuated by gas-rich, well-aligned minor mergers that boosted their mass and ignited new waves of star formation, without introducing the kind of chaotic turbulence that would collapse the disk. There's also a growing body of thought that suggests timing matters. If a galaxy undergoes a major merger early in the universe's history, say, 10 billion years ago, and then experiences a long period of stability, it may have enough time to regrow its disk and re-establish spiral arms. Over such vast timescales, a galaxy can essentially heal from its trauma, reorganize itself, and build a new disk from the residual and infalling gas. Superspirals might be old souls with youthful energy, rebuilt after early turmoil and now stabilized by their massive halos and well-structured dark matter scaffolding. And speaking of dark matter, once again, we must return to its influence. The presence of a massive, stable dark matter halo around a superspiral may be the key to retaining or restoring disk structure after a merger. The halo acts as a gravitational anchor, absorbing some of the energy from the collision and helping to preserve the rotational coherence of the gas. With the halo's help, the galaxy might keep spinning even after absorbing other galaxies, a kind of cosmic gyroscope that helps maintain order amid chaos. Observationally, astronomers are using instruments like the Hubble Space Telescope, ALMA, and now the James Webb Space Telescope to look for signs of past mergers and superspirals, tidal tails, stellar streams, disrupted outer disks. In some cases, these signatures are subtle but present. In others, they're conspicuously absent, suggesting that some superspirals may have never merged at all, or did so under very special, survivable conditions. And then, there's the growing recognition that our traditional view of mergers may be too simplistic. Not all collisions are destructive. Not all growth requires chaos. The universe is full of exceptions, and superspirals may be the ultimate exception, galaxies that grew vast without collapsing, collided without breaking, and transformed without losing their soul. They are, in essence, cosmic paradoxes, forged by forces that usually destroy, shaped by interactions that typically erase order, and yet standing proud with arms outstretched in perfect, radiant symmetry. They remind us that even in a universe defined by entropy, structure can survive. That chaos can birth clarity. That from merger and motion, magnificence can emerge. And in this mystery, we find a deeper truth. Sometimes, the greatest beauty comes not from avoiding collision, but from learning to spin through it, to dance with gravity, to gather from others, and to emerge larger, brighter, and more graceful than before. When we admire a superspiral galaxy, its glittering arms, luminous disk, and spectacular spin, we're only seeing a fraction of the entire structure. The visible portion, though breathtaking, is just the luminous tip of a vast cosmic iceberg. Surrounding every superspiral is something far more immense, mysterious, and utterly invisible, a halo that stretches across hundreds of thousands, even millions, of light years. This halo doesn't shine, doesn't shimmer, and doesn't announce itself with light. And yet, it's fundamental to the very existence of the superspiral it surrounds. The halo of a galaxy, especially a superspiral, isn't just one thing. It's a complex, layered environment made up of dark matter, hot diffuse gas, cool circumgalactic material, and potentially even hidden satellite galaxies. Understanding the nature of these halos, and how they interact with the galaxy inside them, is key to unraveling how superspirals form, survive, and evolve. The dark matter halo, the most dominant component, is the invisible framework that gives the galaxy its shape, its gravity, and its stability. In a typical spiral galaxy like the Milky Way, the dark matter halo is already immense, possibly 10 times more massive than the visible stars and gas. But in superspirals, the halos are truly colossal. Some estimates suggest they may reach masses of 10 to 20 trillion solar masses, with radial extents beyond 1,000,000 light-years. These halos provide the gravitational scaffolding needed to support the enormous rotating disk, preventing it from flying apart due to centrifugal force. But dark matter alone doesn't tell the whole story. These halos are often enveloped in a corona of hot gas, detectable in X-ray observations from telescopes like Chandra and XM Newton. This gas, heated to millions of degrees Kelvin, forms an extended atmosphere around the galaxy, sometimes stretching even farther than the visible disk. In regular spirals, this gas is already difficult to study, but in superspirals, it's even more elusive. Still, the existence of this circumgalactic medium is inferred through absorption lines in the spectra of background quasars, where the gas leaves a faint imprint as it filters starlight. What role does this hot halo gas play? It's more than just a passive cloud. It may act as a regulator of star formation, slowly cooling and condensing into the galaxy's disk, or in some cases, remaining hot and preventing further growth. In superspirals, the sheer mass of the dark matter halo may compress and heat infallen gas to the point that it creates a kind of pressure buffer, shielding the galaxy from disruptive inflows or aggressive stripping by external forces. This thermal cushion could be key to preserving the stability of the disk while still supplying enough material to fuel star formation. Around these galaxies, we also find signs of satellite galaxies, smaller systems orbiting within the gravitational influence of the halo. In the Milky Way, there are dozens of such satellites, from the Magellanic Clouds to the ultra-faint dwarfs that lurk in the halo's outer reaches. Superspirals likely host even more, possibly hundreds of satellite galaxies, some of which may be actively feeding their hosts through tidal stripping or gas transfer. These satellites can be both companions and food sources, supplying fresh material to the central galaxy without disturbing its structure significantly. But halos are more than just containers of material. They also exist within larger cosmic environments. Many superspirals are found in unusual locations, either on the edges of galaxy clusters, in filaments of the cosmic web, or in lower density regions where galaxy interactions are less frequent. This placement may be vital. In a dense cluster environment, galaxies are often stripped of their gas by ram pressure or tidal forces, which would quench star formation and collapse spiral structures. But superspirals seem to occupy a sweet spot, regions with enough isolation to preserve their structure, yet enough proximity to cosmic filaments or gas flows to keep their fuel lines open. It's possible that some of these galaxies lie at the intersections of cosmic filaments, where streams of cold gas are funneled directly into their halos. These intersections act like cosmic crossroads, where the gravitational landscape causes matter to accumulate. Being in such a location would provide an ongoing inflow of both dark matter and baryonic matter, essentially allowing the superspiral to continue growing and feeding over time without the destructive chaos of a dense galaxy cluster. Interestingly, studies of these halos also suggest that angular momentum, the property that keeps galaxies spinning, may be influenced not just by the galaxy's own history, but by the shape and spin of the halo itself. A rotating dark matter halo could impart spin to the baryonic material as it collapses into a disk, potentially explaining why some superspirals have such fast, stable rotations. If the halo is aligned with the galaxy's disk, it may reinforce the spiral structure over billions of years. But the halo is not static. It evolves over time, accumulating material, changing shape, and interacting with its surroundings. In simulations, halo mergers, where two dark matter halos combine, can profoundly affect the galaxy inside. In some cases, they lead to instability or transformation. But in others, they merely increase the mass and binding energy of the system, reinforcing the galaxy's survival potential. Superspirals may represent systems where the halo evolution was smooth and well-aligned, allowing the internal galaxy to grow undisturbed and maintain its spiral shape. Halos may also hold the key to understanding the future of superspirals. As the universe expands, galaxies are pulled away from one another by dark energy, but gravity within halos continues to bind systems together. In the far future, each dark matter halo may become a kind of island universe, isolated from the cosmic web. The properties of a superspiral's halo will determine not only how long it continues to form stars, but how it will age in an increasingly lonely universe. There are even broader mysteries. Could some halos host hidden populations of gas or stars we have yet to detect? Could they conceal primordial black holes, exotic particles, or undiscovered forms of matter? Some cosmologists speculate that the halos of massive galaxies may be windows into new physics, where the behavior of dark matter diverges from what we currently model. In a practical sense, studying these halos is incredibly difficult. They are diffuse, faint, and mostly invisible. Astronomers rely on gravitational lensing, X-ray imaging, spectral absorption lines, and galaxy rotation curves to infer their presence. But every new technique, especially those enabled by next-generation observatories like JWST, Euclid, and the Vera Rubin Observatory, brings us closer to mapping these ghostly giants. And what we're beginning to see is this: superspirals are not isolated anomalies. They are the visible centers of vast, hidden ecosystems, with complex interactions between dark matter, hot gas, cold streams, and satellite companions. Their halos are not just containers, they are engines, shields, and gateways to understanding the fundamental structure of the universe. So while the spiral arms dazzle us with their beauty and motion, and the disks glow with youthful fire, it is the halo, that invisible architecture of gravity and mystery, that makes it all possible. In the shadows beyond the stars, something immense holds it all together. And perhaps, just perhaps, that's where the deepest secrets of the cosmos lie, not in the light we see, but in the darkness that surrounds it. Despite being vastly outnumbered by more typical galaxies, superspirals have a unique trait that makes them disproportionately visible across unimaginable stretches of space. They shine like cosmic lighthouses. Even from billions of light-years away, these rare giants can stand out like beacons in the dark, piercing the cosmic sea with their brilliance. It's an almost poetic contradiction. They're uncommon, yet they're among the easiest galaxies in the universe to spot. But why? The answer lies in a powerful combination of sheer luminosity, spectral characteristics, morphological clarity, and star-forming intensity, all layered atop the advantage of being intrinsically enormous. Superspirals, by definition, are ultraluminous. Many shine with 10 to 100 times the brightness of the Milky Way, radiating across the electromagnetic spectrum, from the cool hum of radio waves to the sizzling glare of ultraviolet light. In visible light alone, some superspirals outshine typical galaxies by a factor of 50 or more. Their integrated luminosities reach values above 10 superscript 1 superscript 2 solar luminosities, numbers usually associated with quasars or starburst galaxies. But unlike quasars, which are bright due to the violent accretion of material into a central black hole, superspirals emit their light across vast disks filled with billions of stars. Their light isn't focused from a single point, it's diffuse, orderly, and extensive. This means they appear large and structured even from across the cosmos. Telescopes don't just detect a pinpoint of brightness. They can see the structure of the arms, the bulge, and sometimes even the warped edges of the disk, depending on distance and resolution. The visual impact is astonishing, a spinning, luminous pinwheel glowing in the black of intergalactic space. Their visibility is further amplified by intense star formation. Superspirals form stars at rates often exceeding 50 to 100 solar masses per year, meaning they're loaded with young, hot, massive stars that emit strongly in the ultraviolet and blue parts of the spectrum. These high-energy stars are short-lived but incredibly luminous, thousands to millions of times brighter than the Sun. When viewed through UV-sensitive instruments like Galactic or the UVIS camera on Hubble, superspirals often appear as dazzling blue structures, alive with newborn stellar clusters. This youth-driven brilliance makes them particularly easy to spot in optical and UV surveys, even when they reside in the distant universe, billions of light-years away. In fact, some superspirals were first identified because their light stood out so sharply in the Sloan Digital Sky Survey (SDSS) and WISE Wide Field Infrared Survey Explorer data. At first, astronomers thought they might be misclassified quasars or artifacts. Only deeper imaging revealed that these were not compact point sources, but rather vast spiral galaxies burning with the light of countless stars. Their infrared emissions also make them ideal targets for deep sky surveys like those from Spitzer, WISE, and now JWST. As their UV and visible light gets redshifted due to the universe's expansion, it shifts into the infrared, where telescopes like JWST excel. This shift doesn't dim the galaxy as much as one might think. Instead, much of its intense star formation is re-emitted as infrared radiation after being absorbed and re-radiated by interstellar dust. So from Earth, we often see these galaxies as infrared powerhouses, blazing even through cosmic dust. Another factor contributing to their visibility is their disk geometry. A spiral galaxy observed face-on offers a larger cross-section of stars and star-forming regions toward the observer. Superspirals, when oriented this way, present a broad, luminous canvas of light. Even if slightly tilted, their large, well-defined arms help differentiate them from featureless ellipticals. The spiral patterns act like visual fingerprints, making them stand out even when their central bulges are lost in distance. Moreover, many of these galaxies reside in relatively low extinction environments, meaning there's less intervening gas and dust between us and them to obscure their light. While some are embedded in clusters or filaments, many sit in less crowded regions, allowing their light to travel relatively unimpeded across the cosmic void. In observational terms, the combination of their size and brightness means that even at redshifts beyond 0.3 to 0.5, superspirals can still be resolved into visible structures with large ground-based telescopes or space-based observatories. In some cases, they rival quasars in brightness, yet they're not point sources. They're entire galaxies, resolved across tens or hundreds of thousands of light-years, visible across time and space. It's this detectability that makes them invaluable to astronomers studying galaxy evolution at high redshift. Because they are easy to spot, even when rare, superspirals become ideal test cases for how massive spiral galaxies formed and evolved. Observing a superspiral 4 billion light-years away is like peering 4 billion years into the past, seeing a massive galaxy in its prime, defying the odds. Even more intriguing is the suggestion that we may be underestimating just how many superspirals there are. Because telescopes have traditionally focused on the most luminous point-like objects, like quasars, or the most massive ellipticals, many superspirals may have been overlooked or misclassified. As our instruments improve in resolution and sensitivity, we may begin to see more of these galaxies lighting up the background of deep field images, once lost in the crowd. The Vera Rubin Observatory, set to begin full operations soon, will scan the entire southern sky repeatedly, capturing time-domain data with unprecedented detail. Combined with JWST's deep infrared sensitivity, these tools could reveal thousands more superspirals, not just in the nearby universe, but pushing toward the epoch of galaxy assembly. Each detection will help us understand not only why they're so visible, but why they exist at all. Ultimately, superspirals are not just easy to see, they are impossible to ignore. They cut through the cosmic night like spinning lanterns, their light encoded with the history of countless stars. Each photon that reaches our telescopes is a messenger from a distant world, a story of gravity, gas, and time, preserved in luminous detail across billions of years. And in spotting these brilliant giants from so far away, we are reminded of one of the universe's great paradoxes, that even the rarest things, when they burn brightly enough, can leave a mark that stretches across the ages. While visible light paints a beautiful portrait of superspirals, revealing their majestic arms, glowing disks, and golden bulges, it's the ultraviolet UV spectrum that reveals their deepest secret, the furious activity of stellar birth happening beneath the surface. Superspirals are not merely luminous for their size, they're radiant with youth. And to truly understand why they shine so intensely, we must look beyond the visible and peer into the UV, where the signatures of hot, young stars blaze most brightly. The ultraviolet light emitted by a galaxy is a direct tracer of massive star formation. Unlike older stars, which emit most of their energy in visible or infrared light, young, high-mass stars, especially O and B-type stars, burn incredibly hot and radiate primarily in the UV. These stars live fast and die young, often burning out in just a few million years. So, when we detect strong UV emissions from a galaxy, we're seeing the footprint of very recent star formation, activity that occurred in the past few million to tens of millions of years. In superspirals, UV surveys such as those conducted by Galaxy Evolution Explorer, have revealed sprawling regions of intense UV activity, especially concentrated along the spiral arms. These arms are not just patterns of stars, they are stellar nurseries, where gas is compressed by density waves, triggering the collapse of molecular clouds and the birth of new stars. The UV light, then, outlines these star-forming regions like neon outlines on a spinning sign, clearly delineating the areas where stellar creation is happening at incredible rates. Galaxy's deep ultraviolet maps showed that many superspirals are UV-bright galaxies, some of them even classified as UV-luminous galaxies, UVLGs, a rare class characterized by exceptionally high ultraviolet output. This UV brightness confirms that their star formation rates are not only elevated, but extraordinary. In many cases, we're talking about tens to hundreds of solar masses worth of new stars forming every year, rivaling or surpassing the most extreme starburst galaxies. What's particularly fascinating is that the UV light isn't confined to the central bulge, or the inner disk. In many superspirals, it extends far into the outer arms, indicating that star formation is not a localized event, but a galaxy-wide phenomenon. These galaxies are forming stars not just in compact bursts, but across hundreds of thousands of light-years, producing a massive canvas of hot, young stars glowing in UV. This makes their disks appear even larger when viewed in the ultraviolet than in visible light, like watching a galaxy expand outward with a blaze of new birth. UV data also reveals important details about the age gradients across the disk. In typical spirals, the inner regions tend to be older and redder, while the outer arms are younger and bluer. Superspirals push this gradient to the extreme. Some exhibit blue UV halos, extending beyond what we'd expect from their visible structure. This suggests not only ongoing star formation but possibly even accretion of new gas in their outskirts, feeding further waves of stellar creation in regions that might otherwise be dormant. The UV spectrum doesn't just show us where stars are forming, it also tells us how they're forming. Spectroscopic studies of UV emission lines provide key information about the metallicity, density, and temperature of the star-forming regions. For example, stronger emissions of lines like C4, and O6 can indicate the presence of extremely hot, massive stars, or even shocks from stellar winds and supernovae. Superspirals often show signs of intense stellar feedback in their UV profiles, indicating that not only are stars forming rapidly, but they're also shaping the environment around them in dramatic ways. There's also another layer to the UV story, the role of dust. Superspirals, with their high star formation rates, are often dusty. Massive young stars emit copious UV radiation, but much of this is absorbed by interstellar dust, which then re-radiates the energy in the infrared. This means that the UV light we see is only part of the picture, the unobscured portion. The UV to IR ratio becomes an important diagnostic tool, It helps astronomers estimate how much star formation is hidden behind dust clouds and how much is directly observable. By combining UV data with infrared observations from instruments like Spitzer, Herschel, or now the James Webb Space Telescope, astronomers can create star formation maps that capture both the visible and the hidden, giving us the full picture of the galaxy's stellar productivity. Superspirals consistently rank among the most energetically active systems in these multi-wavelength studies. Moreover, UV variability studies, tracking how UV light from certain regions changes over time, hint at the episodic nature of star formation in these galaxies. Some superspirals show signs of bursty behavior, where regions light up with star formation and then quiet down, possibly in response to local gas dynamics, feedback events, or even interactions with satellite galaxies. This pattern of galactic breathing could explain how these giants manage their star formation sustainably over long timescales, avoiding the burnout seen in starburst galaxies. Interestingly, the UV properties of superspirals also challenge existing models of spiral galaxy evolution. Most simulations predict that high star formation rates are associated with turbulence, clumpiness, and eventual structural disruption. Yet the UV data shows that superspirals manage to maintain both order and intensity, a kind of controlled chaos in which stellar birth is explosive yet harmonious, widespread yet structurally balanced. And let's not forget the broader implications. Because UV light travels easily across vast cosmic distances, it enables us to spot these galaxies even when they're far away. In deep field observations, it's often the UV signature of a superspiral that first draws attention, a telltale blue glow, distinct from the red or orange fuzziness of old ellipticals. In many cases, UV surveys have flagged galaxies as potential quasars or compact objects, only for deeper imaging to reveal them as monstrously large spirals bursting with star formation. What emerges from all of this is a stunning picture. Superspirals are factories of light, with their most intense production lines blazing in the ultraviolet. They are proof that some galaxies never slow down, never quiet, never age gracefully. Instead, they accelerate, building stars with the fervor of youth across lifespans measured in billions of years. Every flicker of UV light is a whisper from a newborn star, a signal across the void that says, "I am here, and I am burning." In this way, the ultraviolet spectrum becomes a galactic diary, recording each chapter of stellar birth, each rotation of the spiral arms, each wave of creation as it ripples across the galactic sea. In the invisible light of UV, superspirals reveal their heart, a furnace of stars, a map of time, a beacon across the cosmic night. Beneath the magnificent grandeur of a superspiral galaxy, those sweeping arms, radiant disks, and glittering star nurseries, lurks a quieter, often invisible force, the potential presence of a supermassive black hole, nestled deep within the central bulge. These central giants, when actively feeding, can ignite into active galactic nuclei AGN, some of the brightest and most energetic phenomena in the universe. But do superspirals harbor these cosmic engines? And if so, how do they coexist with such orderly, star-forming disks? The answer isn't just fascinating, it's transformative to our understanding of galactic dynamics. In most massive galaxies, there's an almost universal rule: the more massive the galaxy, the more massive the black hole at its center. This correlation, known as the M-sigma relation, ties the mass of the central supermassive black hole to the velocity dispersion of the stars in the galaxy's bulge. So it would seem natural to assume that superspirals, being among the most massive disk galaxies ever found, should contain enormous black holes, possibly tipping the scales at hundreds of millions to billions of solar masses. Observational data supports this assumption. Some superspirals indeed show signatures of active nuclei, X-ray emissions, radio jets, or specific spectral lines like OI or broad H-alpha lines that are dead giveaways of AGN activity. However, what's remarkable is how subtle these signs often are. Unlike the violent, galaxy-wide disruptions seen in some AGN-hosting galaxies, superspirals appear to maintain their structure and continue forming stars even in the presence of an active nucleus. This is a puzzle. AGN, when active, can unleash colossal energy through jets, radiation, and winds. These forces can heat up or blow away surrounding gas, effectively quenching star formation and reshaping the entire host galaxy. In elliptical galaxies or quasar hosts, this kind of feedback is well documented. AGN can act like cosmic regulators, shutting down further stellar birth and accelerating galactic aging. But in superspirals, this does not seem to be the rule. Instead, many appear to harbor active black holes and still support vigorous star formation. How is this possible? There are several working theories, each hinting at the elegant balancing act that superspirals seem to perform. One possibility is that the AGN in superspirals are in a low luminosity or radiatively inefficient phase, meaning they are feeding slowly. These black holes may be massive, but their accretion rates are low, producing only modest outflows and minimal disruption to the surrounding interstellar medium. In this state, the black hole quietly consumes matter, but doesn't generate the kinds of catastrophic winds that would clear the galaxy of gas and halt star formation. Another idea is that feedback from the AGN is directionally constrained. Jets or radiation may be expelled perpendicularly to the disk, venting energy into the galactic halo or intergalactic space instead of through the dense, star-forming arms. This could allow the central black hole to remain active without disrupting the disk, a kind of non-invasive feedback that spares the spiral structure while still regulating the core environment. There's also the concept of coexistence through cycles. AGN activity isn't constant, it can turn on and off over timescales of tens to hundreds of millions of years. A superspiral might undergo bursts of AGN activity, during which central gas is heated or ejected, followed by quieter periods where gas cools, falls back into the disk, and reignites star formation. Over cosmic timescales, this ebb and flow of energy may allow the galaxy to self-regulate, keeping both the black hole and the stellar nursery in check. Interestingly, some superspirals appear to lack strong AGN signals entirely, despite having the mass and structure that would suggest the presence of a large black hole. This raises the possibility that some of them host dormant supermassive black holes, present, but not currently accreting matter. They may have gone through active phases in the past, but are now in a quiescent state, quietly waiting for new gas to fall inward. This would also help explain the lack of central disruption and the continued star formation across their disks. But when AGN are present, they leave behind subtle, yet telling, fingerprints. High-resolution spectroscopy reveals ionization cones, faint beams of radiation streaming out from the galactic center. X-ray data from Chandra and new stars shows compact nuclear sources. Radio observations from VLA and ALMA sometimes detect small jets or lobes, weak but present. And infrared data from Spitzer or JWST often reveals warm dust heated by a central engine, even when the AGN is too obscured to see directly. What makes this even more intriguing is the role that AGN may play in the growth and evolution of superspirals themselves. A moderate level of AGN activity may actually stimulate star formation, especially in the early phases of a galaxy's life. Known as positive feedback, this process involves AGN-driven outflows compressing nearby gas, triggering the collapse of clouds and the ignition of new stars. In superspirals, where the gas supply is massive and widespread, this mechanism might operate across large regions, boosting their already prodigious star formation rates. Moreover, AGN may act as governors, ensuring that gas inflows don't overwhelm the galaxy. By periodically heating or redirecting infalling material, the central black hole may help stabilize the disk and prevent runaway starbursts that would otherwise burn through the galaxy's gas too quickly. In this view, the black hole isn't just a destroyer, it's a moderator, orchestrating a delicate balance between growth and sustainability. It's also worth considering the idea that superspirals and their black holes have co-evolved, growing together over billions of years. As the galaxy's mass increased, so did the black holes. But instead of the black hole overtaking its host and suppressing activity, a kind of mutual harmony emerged. This scenario suggests a refined, perhaps even fine-tuned relationship between the galactic disk and the central black hole, one that's very different from what we see in elliptical galaxies, where the black hole often dominates and suppresses the rest of the galaxy. This coevolution raises profound questions about how and when black holes form in such galaxies. Did superspirals begin with small black holes that gradually grew through accretion and mergers? Or were they seeded early in the universe with massive primordial black holes, growing alongside the disk from the very beginning? And more importantly, do the properties of the superspiral shape the behavior of the black hole, or vice versa? We are only beginning to scratch the surface of these mysteries. As telescopes like JWST, Athena, and the extremely large telescope, ELT, come online, they will give us deeper insight into the inner workings of these galaxies. With higher resolution spectra and more sensitive imaging, astronomers will soon be able to peer into the very hearts of superspirals, mapping the accretion flows, measuring black hole masses directly, and unraveling the tangled feedback processes that connect core to cosmos. For now, what we know is this: superspirals may host some of the universe's most powerful engines, but instead of tearing themselves apart, they seem to integrate these engines into a larger, stable system. They hold their shape. They grow. They spin. They burn with youthful light, all while carrying the heavy, silent weight of a black hole at their core. And in this quiet symphony of gravity, matter, and energy, they teach us a new lesson: that power does not always destroy, and that even the most formidable forces in the universe can be part of something beautiful, stable, and surprisingly gentle. The environments that superspiral galaxies inhabit offer crucial clues about their formation, evolution, and survival. After all, no galaxy is an island. Every one of them exists within a broader cosmic landscape shaped by gravity, gas flows, dark matter filaments, and the subtle dance of nearby companions. For typical spirals and ellipticals, location often dictates fate. But what about these rare giants? Are superspirals the rulers of dense galaxy clusters, or are they solitary monarchs drifting through cosmic wilderness? This question is more than geographical. It goes to the heart of how superspirals defy the expected outcomes of their mass and morphology. In standard galaxy evolution models, high-mass galaxies, particularly those above a few 100 billion solar masses, tend to evolve into elliptical galaxies through mergers and violent interactions. And these interactions are most common in dense environments, such as galaxy clusters. Spirals, by contrast, are more commonly found in lower density regions, where they can avoid frequent mergers and retain their delicate disk structures. So the discovery that some of the most massive galaxies in the known universe are not ellipticals but spirals, and superspirals, at that, immediately raises questions about where they live. Initial surveys, including those from the Sloan Digital Sky Survey (SDSS), suggested that many superspirals are located in relatively low to intermediate density environments, cosmic suburbs, if you will. These are not the chaotic, crowded centers of rich clusters like the Coma cluster, where galaxies are constantly pulled, stripped, and slammed together. Instead, they're found on the edges of galaxy clusters, in galaxy groups, or even in isolated pockets along filaments of the cosmic web. This intermediate setting may be precisely why they survive as spirals. In the crowded heart of a cluster, gravitational harassment, tidal forces, and ram pressure stripping by the hot intracluster medium are nearly unavoidable. Spiral structures in such regions are frequently destroyed, their gas removed, their disks heated or disrupted. Star formation shuts down, and over billions of years, the galaxy transforms into a featureless elliptical or lenticular remnant. But in moderately dense regions, galaxies may have enough gravitational neighbors to fuel growth through minor mergers or gas infall, while still avoiding the destructive chaos of a high-density core. This allows for continued gas accretion, ongoing star formation, and the preservation of spiral structure on truly massive scales. But that's not the whole story. Not all superspirals are isolated. A small number have been discovered in more densely populated environments, even in cluster outskirts or filament junctions, where galaxies and gas are funneled together by the large-scale structure of the universe. These locations can provide streams of cold gas, channeled through dark matter filaments, directly into the galaxy. This infall may be part of the reason why superspirals can maintain their immense gas supplies and sustain high star formation rates over long timescales. In some cases, superspirals appear to act as central galaxies in small groups or subclusters, the largest and brightest members of their local environment, surrounded by smaller satellite galaxies. These satellites may orbit quietly or contribute their gas through tidal stripping, minor mergers, or cold accretion events. In such a setting, the superspiral plays the role of a cluster king, but not in the classical sense of a central elliptical galaxy dominating a massive cluster. Instead, it governs a looser, more spiral-friendly kingdom, where conditions are ideal for long-lived disk galaxies to flourish. It's also worth noting that in some rare cases, superspirals do show signs of interactions or mergers, but without losing their spiral structure. These interactions may be grazing or glancing, not full head-on collisions, and therefore provide gas and angular momentum without triggering total disk collapse. This might suggest a new class of environment-driven evolution, where certain types of interactions actually help build rather than destroy spiral giants. In this way, superspirals may be the products of well-timed interactions in the right environments, accumulating mass without losing structure. Interestingly, simulations of cosmic structure formation, such as those run by the illustrious TNG or Eagle projects, have begun to show that the distribution of angular momentum and gas flows in different parts of the universe is highly non-uniform. Certain regions, especially at the intersections of filaments, may be more likely to form high-spin halos with cold gas accretion, the perfect ingredients for massive spiral galaxy formation. Superspirals may be the rare beneficiaries of this large-scale geometry, having formed and grown in angular momentum-rich zones, shielded from the more disruptive tidal chaos found elsewhere. Moreover, these galaxies seem to avoid the most extreme environments. In rich clusters, the high velocities of galaxies make mergers less common, and the hot gas environment strips away cold gas reservoirs. Very few, if any, superspirals have been confirmed as central galaxies of rich clusters. When spirals do live in such clusters, they often exhibit signs of disturbance, quenched star formation, or morphological transition. This absence of superspirals in these regions reinforces the idea that their survival depends critically on where they live. But perhaps the most profound implication of their environment is what it tells us about cosmic balance. Superspirals seem to represent a Goldilocks scenario in galactic evolution, not too hot, not too cold, not too dense, not too sparse. Their environments are dense enough to supply gas, dynamic enough to support growth, yet gentle enough to preserve structure. They sit at the intersection of gravitational potential wells, angular momentum conservation, and gas supply sustainability. Future surveys, particularly with the Rarity, Rubin Observatory and Euclid, will help map the environments of superspirals in unprecedented detail. By correlating their locations with large-scale structure maps, researchers hope to determine whether these galaxies are preferentially located at cosmic web nodes, in void walls, or along specific filaments. Spectroscopic follow-ups will reveal how their satellites interact with them, and how their motions relate to the surrounding dark matter halo. Already, studies are revealing hints that some superspirals may be on their way to becoming dominant central galaxies, the future kings of evolving groups or clusters. But for now, many remain cosmic loners, spinning elegantly through space with few close rivals, their light a testament to a long, uninterrupted life of formation, motion, and brilliance. Their homes, then, are either fully crowded nor entirely empty. Instead, they seem to reside at the cosmic edges, places where growth is still possible, but destruction has not yet arrived. In this frontier, superspirals are both survivors and pioneers. They are monuments to balance, thriving in the thin margins of the universe's great structures. And perhaps that's what makes them even more fascinating, not just what they are, but where they are, whispering stories from the quiet corners of a violent universe. In astronomy, one of the most powerful tools for understanding galaxies comes not from looking at individual cases but from discovering patterns, relationships that seem to hold true across vast samples and epochs. These patterns are known as scaling relations, and they underpin much of what we believe about how galaxies form, grow, and evolve. They allow astronomers to estimate the mass of a galaxy from how fast it spins, or its luminosity from its size. But when it comes to superspirals, these elegant rules, carefully observed and calibrated over decades, begin to break. One of the most important, and long-established scaling relations for spiral galaxies is the Tully-Fisher relation. This empirical law links the luminosity of a spiral galaxy to its rotational velocity. Simply put, the faster a galaxy spins, the brighter it is. This relation has been critical in everything from calculating galaxy distances to understanding dark matter distribution. It works remarkably well for normal-sized spirals, including the Milky Way and Andromeda. But superspirals, in their enormous scale and staggering brightness, refuse to fall in line. When plotted on the Tully-Fisher diagram, superspirals consistently lie above the expected curve. Their rotation speeds are certainly high, some exceeding 400 km per second, compared to the Milky Way's roughly 220 km per second, but their luminosities are disproportionately extreme. Many shine 10 to 50 times brighter than galaxies with comparable rotational speeds. This means that if you use the Tully-Fisher relation to estimate a superspiral's brightness based on its rotation, you'd vastly underestimate it. This mismatch hints at something deeper than observational error. It suggests that the internal physics and evolutionary pathways of superspirals differ fundamentally from those of ordinary disk galaxies. Their excess luminosity implies either a massive stellar population, a high rate of ongoing star formation, or unusual efficiencies in converting gas into stars. Or perhaps all three at once. Other scaling relations don't fare much better. The mass-size relation, which states that more massive galaxies should have correspondingly larger disks, seems stretched beyond its limits in superspirals. Some of these galaxies have stellar masses exceeding 10 superscript 1 superscript 2 solar masses, comparable to or even greater than many elliptical galaxies, but retain flat, extended spiral disks stretching over 500,000 light-years. This is 10 to 20 times the diameter of the Milky Way. According to conventional models, galaxies with such mass should have long since collapsed into spheroids, often through major mergers or internal instabilities. But here they are, vast, serene, and spinning. Then there's the surface brightness relation, which usually follows that as a galaxy grows larger, its average surface brightness tends to decrease, simply because the light is spread over a bigger area. Again, superspirals break this rule. Despite their enormous size, many maintain high surface brightness across their disks. This could mean that their stellar mass is distributed unusually efficiently, or that star formation is still actively replenishing the disk's brightness even in its outermost regions. In any case, the expected fade that comes with galactic sprawl just doesn't seem to apply here. The mass-metallicity relation, another cornerstone of galaxy evolution theory, may also be challenged. Typically, galaxies with more mass have higher metallicity, a result of recycling material from many generations of stars. Yet some superspirals show evidence of moderately enriched gas, suggesting that even at their size, they're still accreting relatively pristine material from the cosmic web. This could imply a longer-lasting gas infall phase, or that their internal feedback mechanisms are more complex and regulated than expected. The implications of all this go far beyond anomalies on a plot. These scaling relation breakdowns call into question the universality of the laws that describe galaxy formation. The fact that superspirals lie so far off the charts might mean that we're seeing a different mode of galactic evolution, one where the mechanisms of growth, star formation, feedback, and angular momentum conservation work in a regime we're only beginning to understand. Some theorists have proposed that superspirals represent a third population, distinct from both classical spirals and massive ellipticals. They might be the result of extreme but finely balanced conditions, massive enough to gather enormous halos of gas and dark matter, but stable and isolated enough to retain their disk structure without collapsing or fragmenting. This might make them natural outliers, rare products of perfect cosmic timing and geography. Others suggest they are the endpoints of spiral galaxy evolution, galaxies that somehow avoided the fate of merger-driven ellipticals by maintaining their spin and gas supply over billions of years. In this view, superspirals aren't breaking the rules, they're rewriting them. They hint that the simple relationships we use to describe galaxy properties might actually bend under certain conditions, or that more complex dynamics, like the interplay between gas accretion, dark matter halos, and angular momentum, dominate in ways we haven't yet modeled correctly. These anomalies also have implications for cosmology and large-scale structure surveys. If scaling relations don't hold at the extreme high mass end, then assumptions baked into models of galaxy clustering, star formation history, and even dark matter distribution may need revision. Surveys that rely on these relations to infer galaxy properties from limited data might be underestimating or misclassifying massive disk galaxies entirely. And of course, this has practical consequences too. Imagine peering into a deep field image of the early universe, detecting a high redshift galaxy with an unexpectedly high luminosity. Using standard relations, we might assume it's a quasar or a starburst elliptical. But what if it's a super spiral in the making, an outlier that our models can't yet account for? In this way, super spirals are not just cosmic curiosities. They are stress tests for our theories, forcing us to examine the boundaries of what we thought was possible. Their very existence suggests that the universe is more versatile and inventive than we dared to believe. The tidy relationships we once drew between rotation, mass, light, and size may only be approximations of a far more intricate reality. As more of these giants are discovered and studied in greater detail, especially with tools like the James Webb Space Telescope, ALMA, and the upcoming Vera C. Rubin Observatory, will likely gain the data needed to reshape our scaling models or perhaps define new families of galaxies with their own unique laws. It's a reminder that in the cosmos, rules are often made to be broken, or at least, to be reinterpreted through the lens of the extraordinary. And in breaking these rules, super spirals do more than challenge theory. They expand imagination, showing us that the universe is not limited by our frameworks. It invents, it surprises, and in galaxies like these, it whispers that not all paths to greatness follow the usual road. The survival of spiral structure in super spirals is, in many ways, the most astonishing part of their story. We expect spiral galaxies to be relatively fragile, elegant yet susceptible to disruption. As galaxies grow more massive, accumulate more gas, undergo mergers, or simply age, their spiral patterns usually break down. Disks warp, arms dissolve, and the entire system can puff up into a featureless elliptical blob. That's the standard picture. And yet, here are these super spirals, 10 times larger and more massive than the Milky Way, bursting with star formation, and still retaining those delicate, sweeping spiral arms. How? What physical forces have allowed these giants not just to survive, but to remain orderly? To answer that, we must start by understanding what makes spiral structure possible in the first place. In typical spirals, the arms are not static. They're density waves, like traffic jams in space. Stars and gas orbit the galactic center, moving in and out of these density waves, which compress gas and trigger star formation as they pass. The whole structure is stabilized by a balance between gravity, angular momentum, and gas dynamics. But this balance is delicate. Too many gravitational disturbances, especially from galactic mergers, close flybys, or violent internal instabilities, can easily disrupt the disk and destroy the spiral pattern. The more mass a galaxy accumulates, the more susceptible it becomes to dynamical heating, a process that thickens the disk and erases its structure. That's why it's so rare to find a massive galaxy that still retains its spiral form. Most galaxies that pass a certain mass threshold, typically around 10 superscript 1 solar masses, eventually become elliptical due to major mergers or internal collapse. Yet superspirals, with masses that can exceed 10 superscript 1 superscript 2 solar masses, buck that trend entirely. One reason they might remain spirals is that they've avoided major mergers, or experienced only carefully tuned minor mergers that enhance their growth without destabilizing the disk. Mergers are the primary mechanism by which spirals are transformed into ellipticals. If a super spiral managed to accrete mass gradually, through steady gas inflows, minor interactions, or cold accretion from filaments, then it could grow to immense size while keeping its angular momentum intact. Angular momentum is critical. Spirals form and remain spirals because they spin. The entire disk structure depends on rotation speed and conservation of angular momentum. If a galaxy loses angular momentum, either through mergers or internal friction, its stars stop orbiting in an orderly disk and begin moving in random, elliptical orbits. That's when the disk collapses and transforms into a spheroid. But superspirals appear to retain high angular momentum even at extreme mass. In fact, their spin rates often exceed those of smaller spirals, with rotation curves that remain flat or even rise at extreme radii. That alone can help preserve the disk. If they formed in high-spin dark matter halos, those initial conditions might have given them the angular momentum needed to grow large while keeping a disk-like shape. Computer simulations like those from the Illustrious and Eagle projects have begun to show that galaxies forming in specific halo configurations, with high spin and stable, low-density environments, can indeed reach enormous sizes without ever undergoing the kind of disruptive mergers that would destroy spiral arms. These simulations suggest that cosmic environment matters deeply, wherein how a galaxy forms determines whether it will retain its disk or dissolve into chaos. Another factor is gas accretion. Superspirals likely sit in regions of the cosmic web where cold gas can stream into the galaxy smoothly, replenishing the disk without triggering massive starbursts or collapse. This inflow feeds star formation and helps preserve the disk's thinness and rotation. Without this continuous fuel supply, the spiral arms would slowly fade, and the galaxy might become a more passive, puffed-up system. Superspirals also seem to benefit from stabilizing feedback mechanisms. While some have weak AGN activity, they rarely exhibit the kind of explosive feedback that would blow apart the interstellar medium or disrupt disk rotation. Instead, their black holes may act as modulators, gently heating the core or regulating inflows in ways that promote structure over time. Then there's the distribution of mass. In many superspirals, the stellar mass is spread over a huge radius, lowering the average surface density and preventing gravitational collapse. The disk is extended and relatively diffuse, allowing spiral waves to persist without fragmenting into chaos. Some studies also suggest that thicker disks, which some superspirals appear to have, are actually more stable against disruptive instabilities. They're not as fragile as thin, gas-rich disks like that of the Milky Way. This mass distribution may also be influenced by dark matter halos. In spirals, dark matter plays a key role in flattening the rotation curve, extending the region of stable orbital motion far beyond the visible disk. Superspirals likely reside in enormous halos, possibly larger than those of any other galaxy type. These halos not only contribute to rotation but also dampen gravitational interactions, absorbing or diffusing potential disturbances that might otherwise ripple through the disk. But perhaps most remarkably, superspirals appear to self-regulate. They're not static objects, they're dynamic systems in balance. Feedback from star formation and low-level AGN activity prevents runaway growth or collapse. Gas inflows replenish but don't flood the system. Disk rotation maintains order while allowing for spiral wave propagation. The result is a kind of galactic homeostasis, where massive forces are constantly active, but never out of control. It's also worth considering that we may be seeing superspirals in a specific phase of their evolution, a kind of late-stage spiral dominance. They may not remain this way forever. Given a few billion more years, some may still transform into elliptical systems, especially if environmental conditions change. But for now, they offer a rare snapshot of what happens when a galaxy grows vast, luminous, and powerful, yet still retains the delicate imprint of rotation and spiral form. And in doing so, they force us to reconsider our assumptions. Spiral structure, we thought, was the hallmark of youth and fragility. But superspirals prove it can also be the mark of endurance and balance, a sign that not all that grows must unravel. Here, gravity is not a destroyer but a sculptor, carving perfect patterns into galaxies that should, by all rights, have lost their form. Instead, they remain, spinning, orderly, and beautiful, against all odds. To understand the true scale and majesty of superspiral galaxies, we need only hold up our own Milky Way as a mirror. The Milky Way is often considered a grand and impressive spiral in its own right. It spans roughly 100,000 light-years in diameter, hosts more than 100 billion stars, and possesses a stellar mass of around 10 superscript 1 solar masses. To us, it feels like the definition of a vast galaxy. And yet, when placed beside a superspiral, our galaxy looks modest, ordinary, even a little small. Let's start with sheer size. Some superspirals span 400,000 to 500,000 light-years across, up to 5 times larger in diameter than the Milky Way. That difference in diameter translates to a vastly greater surface area, allowing for more stars, more gas, and more complex structures. Their disks aren't just wider, they are also more extended in terms of spiral arm reach, star-forming zones, and gas envelopes. The Milky Way, by comparison, appears more compact and conservative, like a coiled spring compared to a sprawling, luminous tapestry. The contrast grows more striking when we look at mass. While our galaxy's stellar mass is estimated at around 100 billion to 400 billion solar masses, some superspirals exceed 1 to 2 trillion solar masses in stars alone, and that's not including dark matter. This makes them at least 5 to 10 times more massive than the Milky Way. And yet, despite this tremendous weight, many superspirals continue to rotate smoothly, form stars prolifically, and maintain a thin, elegant disk structure. In comparison, the Milky Way feels like it's cruising in economy class while these giants are flying first class at galactic scale. Then there's luminosity, the total amount of light a galaxy emits. The Milky Way, while radiant, is not even among the brightest spiral galaxies in the universe. Its absolute magnitude is around -21, making it roughly average by spiral galaxy standards. Superspirals, however, can shine with absolute magnitudes of -23 or brighter, meaning they can emit 10 to 20 times more light than the Milky Way. This immense luminosity isn't just the result of size, it's also due to their high rates of star formation and the presence of many massive, young, blue stars that radiate intensely across multiple wavelengths. Our galaxy forms stars at a relatively modest rate, about 1 to 3 solar masses per year. That's good enough to maintain steady growth and replenish its stellar population over billions of years. But superspirals can churn out 10, 20, even 50 solar masses of new stars per year, placing them closer to starburst galaxies in terms of activity. Their gas reserves are more abundant and more efficiently converted into new stars, particularly in the sprawling outer arms and mid-disk regions. These are stellar factories, whereas the Milky Way feels more like a well-managed workshop. Despite this, the Milky Way isn't underachieving, it's actually quite balanced for its environment. It resides in a small group of galaxies, the local group, with relatively few neighbors to interact with. Its growth has been gradual and non-violent, preserving its structure and allowing it to remain a beautiful barred spiral. In that sense, it's representative of what we might call a standard spiral evolutionary path, steady, long-lived, and stable. But superspirals represent a different trajectory, an extreme one. They are examples of what happens when a spiral galaxy grows big and fast, accumulating mass, gas, and angular momentum in massive quantities without tipping into chaos. They defy the usual growth limits and remain elegant even when stretched to cosmic extremes. Their dark matter halos, too, are in another league. While the Milky Way's halo is estimated to be around 1 to 2 trillion solar masses, a superspiral's halo might be several times larger, giving it the gravitational stability to support a larger disk and more extended gas reservoir. That extra dark matter also flattens the rotation curve out to greater distances, allowing the spiral arms to maintain cohesion across enormous scales. And yet, with all this greatness, there's a poetic humility to our Milky Way. While it may seem small in comparison, it is far more typical, a member of the quiet majority of spiral galaxies in the cosmos. Its structure is well studied, its rotation well measured, its satellites well mapped. And unlike many distant superspirals, we can study it from the inside, star by star, arm by arm. The Milky Way may not be the loudest or brightest, but it is our cosmic home, and arguably, our best teacher. Comparing the two brings clarity. The Milky Way shows us what's normal, what's expected. Superspirals show us what's possible, the outliers that push the limits of scale, brightness, and structure. They exist at the fringes of our models, but they're real. And they remind us that the universe doesn't always follow the rules in a predictable way. Imagine placing our solar system within a superspiral. Our Sun, currently in the quiet suburbs of the Milky Way, would be even further from the galactic core, lost among even more distant spiral arms and stellar clusters. The sky might shimmer with even denser fields of stars. The interstellar medium would be more active. The galaxy's core might blaze more brightly in the night sky. Everything, every cosmic yardstick, would be magnified. And yet Earth would still be Earth. Life would still unfold. The cosmos doesn't require grandeur to support complexity. But superspirals give us a glimpse of grandeur on an almost unimaginable scale, the universe showing off, as if to say, this too is what a galaxy can be. In the end, when we look at the Milky Way next to a superspiral, we're not seeing one as better than the other. We're seeing the diversity of cosmic architecture, the range of what gravity, gas, and time can build. From the quiet middleweights like our home galaxy to the colossal titans of spiral form, the universe offers a breathtaking spectrum of galactic wonder. And in that spectrum, we find a deeper appreciation not just for what makes superspirals magnificent, but for what makes our own Milky Way modest, balanced, and enduring, equally extraordinary in its own right. Superspirals are not just fascinating outliers. They are active challenges to some of the most fundamental ideas in galaxy evolution theory. For decades, astronomers believed that galaxies followed a somewhat predictable evolutionary path, guided by mass, environment, and time. A small galaxy might form as a spiral, slowly accumulate mass, interact with neighbors, undergo mergers, and eventually morph into a more spheroidal, passive object, a typical elliptical galaxy. This sequence, known as the Hubble sequence, has long shaped our understanding of how galaxies grow and transform. But then came the superspirals, massive, ultraluminous, hyperstructured spirals, and suddenly, everything seemed less certain. Superspirals represent a paradox. They have the mass and brightness we associate with elliptical galaxies, yet they retain the elegant, rotating disk structure of spirals. According to prevailing models, galaxies that grow to such extremes of size and mass should inevitably undergo mergers, especially in denser environments, and these interactions should destroy the ordered motion of a disk. Stars should be flung into random orbits, gas should be stripped or ignited in a central starburst, and the spiral form should collapse into an elliptical profile. But these colossal spirals didn't get the memo. They somehow grew immense without surrendering to chaos. They didn't collapse, didn't lose their disks, didn't become red and dead. Instead, they remained graceful, dynamic, and actively forming stars. This suggests that the traditional view of galactic life cycles, as a kind of inevitable gravitational aging process, might be incomplete. In particular, superspirals indicate that spiral galaxies can grow larger, live longer, and remain more structured than we ever thought possible. One major implication of this is that mergers may not be as dominant a mechanism in galactic transformation as previously assumed, at least, not in all cases. While major mergers have long been seen as the primary way that spirals turn into ellipticals, the existence of superspirals implies that some galaxies can grow massive without undergoing major disruption. This hints at the existence of alternative evolutionary pathways, routes where galaxies evolve through steady gas accretion, minor mergers, and internal regulation, maintaining their disk structure while still reaching enormous sizes. This challenges another pillar of galactic evolution theory, the so-called quenching of star formation. The Standard Model holds that as galaxies become more massive, various feedback mechanisms, such as AGN activity, supernova winds, or hot halo gas, shut down star formation by heating or expelling cold gas. The galaxy transitions from blue and star forming to red and dead. But superspirals are both massive and blue. They're not just forming stars, they're forming them at incredible rates. This suggests that quenching isn't universal, and that under certain conditions, even the most massive galaxies can continue to thrive. In fact, some researchers now speculate that superspirals may represent a distinct phase or branch in galaxy evolution, one that's been underrepresented in simulations and underdetected in observations. Our existing models, built largely from semi-analytic frameworks and large-scale hydrodynamical simulations, often fail to predict such galaxies with any frequency. Either the simulated galaxies grow too fast and collapse into ellipticals, or they fail to sustain the star formation necessary to remain luminous. Superspirals, therefore, expose a blind spot in how we model gas flows, angular momentum retention, and environmental impact over time. Moreover, these galaxies raise critical questions about the role of dark matter halos in shaping galaxy evolution. For a superspiral to remain coherent at such large scales, its host dark matter halo must not only be enormous, but also highly stable and possibly unusually high in angular momentum. This runs counter to many assumptions in structure formation theory, where halo spin parameters are thought to follow a narrow distribution. If superspirals form in rare, high-spin halos, then they offer clues about variations in the cosmic web, hints that some regions of the universe may be pre-tuned to produce galaxies of exceptional form and function. Their rarity also matters. The fact that we've found only a few dozen superspirals out of the hundreds of thousands of galaxies catalogued in surveys like SDSS and Gamma suggests they are extraordinary events. They are not simply scaled-up versions of ordinary spirals. They are exceptional products of exceptional conditions. This scarcity further supports the idea that multiple evolutionary tracks must coexist in the universe. Some galaxies follow the well-worn path toward ellipticals, while a rare few tread the spiral path to extremes. This forces theorists to reconsider the rigidity of the Hubble sequence. Rather than a linear progression from disk to spheroid, galaxy evolution may be a branching process, with diverse endpoints. Superspirals may not be transition objects, they may be endpoints themselves, the final form of a long, uninterrupted spiral lineage. Their impact isn't just theoretical. As we peer further into the universe with next-generation telescopes like the James Webb Space Telescope, JWST, and the upcoming Vera-C, Rubin Observatory, we may find analogues of superspirals at earlier cosmic epochs. If we do, it could radically revise our understanding of when and how galaxy morphology diversified. It might turn out that spirals didn't just fade away as the universe aged. Some may have continued growing, spinning, and blazing, challenging our entire concept of a galaxy's natural lifespan. And then there's the human dimension. Superspirals are reminders that the universe still holds surprises, that the maps we've drawn of cosmic evolution aren't complete. They invite humility in the face of the cosmos. For every tidy rule we've written, there are galaxies out there scribbling in the margins, drawing their own conclusions in light and spin. They tell us that growth doesn't always mean collapse, that order can survive even under cosmic strain, and that the story of galaxies isn't just about transformation and death, but also about resilience, balance, and defiance. In that defiance, superspirals are more than physical structures. They're messages, testaments to nature's creativity, complexity, and refusal to be boxed in. And in rewriting the rules of galactic evolution, they remind us that the universe is not a finished book, but a draft still being written in starlight. As we delve deeper into the nature of superspiral galaxies, a compelling question rises from the swirl of data and cosmic awe. Are these galaxies the final form of spiral evolution? Could superspirals represent the endgame, the terminal, most advanced stage of disk galaxy development? It's a question that doesn't just touch on their structure, but challenges our broader understanding of how galaxies grow, age, and ultimately settle into their final roles within the universe. To consider superspirals as end-stage galaxies, we need to examine not just their size or brightness, but their dynamical stability, ongoing star formation, environmental history, and ability to resist collapse. In all of these aspects, superspirals appear not just mature, but masterfully balanced. Their size and mass place them among the most extreme galactic entities known to exist, not just bigger, but more ordered than most. Yet unlike chaotic starbursts or the exhausted remnants of elliptical galaxies, they continue to thrive, spinning gracefully while creating stars at high but regulated rates. If galaxies follow evolutionary paths like living organisms, then most spirals begin life with gas-rich youth, transition through middle-aged star formation, and eventually lose their gas and structure through mergers or environmental stripping, becoming more spheroidal, passive systems. But superspirals seem to have avoided, or delayed, that fate. They have maintained their disks, retained their gas, and somehow continued to build stars across gigayears, suggesting a long-lived spiral adulthood that might not lead to the usual quiet end. In this sense, superspirals could be thought of as immortal spirals, galaxies that have avoided the traditional aging process by sidestepping or surviving the forces that typically bring spiral evolution to a halt. Their massive dark matter halos provide them with the gravitational backbone needed to support extended disk structures. Their high angular momentum preserves orderly rotation. And their sustained gas inflow keeps the engine of star formation running even when other galaxies have long gone dormant. It's as if they've reached a kind of galactic equilibrium, where all the major forces, gravitational, thermal, radiative, and kinetic, have reached a stable configuration. This balance allows them to persist, perhaps for billions more years, without collapsing into an elliptical or fading into a ghost of their former selves. Some astronomers even speculate that, under the right conditions, a superspiral could remain active until the universe itself grows cold and dark, evolving only slowly, perhaps thickening its disk slightly, or forming a more massive bulge, but never truly collapsing or transforming. They may eventually run out of gas, and star formation will slow, but if they maintain their structure, they'll become something akin to passive spiral fossils, vast, ancient disks full of old stars, still spinning, still structured, long after the cosmic fireworks have faded. This opens the door to the possibility that superspirals aren't a transitional state, but a terminal morphology. In this view, some galaxies don't follow the path from spiral to elliptical at all. Instead, they evolve from dwarf disks to regular spirals, to giants, to superspirals, and then simply stay there, slowly dimming as the cosmic gas supply dwindles. They represent a complete evolutionary path in their own right, running parallel to, but distinct from, the path that leads to the elliptical giants found in galaxy clusters. There's also the idea that superspirals are cosmic exceptions rather than rules. That is, most galaxies might still follow the spiral to elliptical pathway, but a few, due to unique initial conditions, stable environments, and favorable inflow histories, manage to avoid the disruptions that trigger transformation. These few become the cosmic elite, the best-case scenario of spiral evolution, reaching their peak form without ever having to lose their identity. What makes this concept even more intriguing is that superspirals, despite their strength and scale, might still be vulnerable to eventual disruption. Over billions of years, they may fall into larger structures like galaxy clusters, where gravitational harassment, hot gas, and tidal forces could still strip them of gas and destroy their disks. In this sense, even if they are the final form, it might be a temporary final form, one that persists until the right, or wrong, environment triggers its transformation. Still, their current existence implies a resilience that defies the odds. If they are the culmination of a spiral's evolutionary journey, then they reveal that some galaxies can grow vast, luminous, and dynamically rich without becoming chaotic or exhausted. They show that spiral evolution can continue longer than we imagined, and that disk galaxies can become giants without self-destructing in the process. Looking forward, upcoming observatories and simulations will help answer whether these galaxies are terminal products, rare transitions, or exquisite detours in the cosmic narrative. The Vera Rubin Observatory will track faint disk structures and reveal superspirals at more varied redshifts. The James Webb Space Telescope might glimpse early analogues of these galaxies in the distant universe, showing us whether they formed early and endured or are newer, late-stage phenomena. And even deeper questions await. Could these galaxies be home to unique stellar populations, or host unusual planet-forming environments? Could their extreme size and stability allow for habitable zones that persist longer than those in other galaxies? Might life in a superspiral be more likely to arise, or to last, because of the galaxy's extended lifespan and stable disk? If the answer is yes, then not only are superspirals the endgame for galactic structure, but they might also be guardians of longevity, havens of cosmic balance where stars, planets, and potentially life can persist longer than anywhere else. In the cosmic game of evolution, the rules are clear but flexible. Ellipticals are efficient, spirals are elegant, dwarfs are ubiquitous. But super spirals? They are the boss level, the galaxies that beat the game without breaking the board. And if they are indeed the endgame, they don't go out in collapse or chaos. They end with order, structure, and a brilliance that refuses to fade. The sheer size, luminosity, and star-forming activity of super-spiral galaxies raise fascinating questions about not just cosmic structure, but also the potential for life. If the Milky Way, with its relatively modest size and star formation rate, can host a life-bearing planet like Earth, what possibilities might exist in galaxies that are 10 times more massive, forming stars at rates 20 times faster, and containing hundreds of billions more stars? Could superspirals be cradles of life, scattered across the cosmos, hiding more habitable planets than any other type of galaxy? To answer this, we have to examine the conditions necessary for life, especially complex life, and how those conditions might be affected by the extreme nature of superspirals. First, let's look at stellar abundance. The more stars a galaxy contains, the more chances it has to host planetary systems. Superspirals, with their trillions of stars, likely host trillions of planets as well. This sheer numerical advantage is staggering. If only 1 in 1,000 stars had an Earth-like planet, and only 1 in 1,000 of those developed life, a superspiral might still host billions of living worlds. In this sense, they are like galactic rainforests, immense ecosystems of stars and planets, teeming with potential. But it's not just the number of stars that matters, it's what kinds of stars they are, and where they are located. Superspirals are actively forming stars at a rapid pace. That means many of their stars are young, massive, and hot, especially in the spiral arms, where dense gas clouds collapse into new stars. These massive stars emit intense ultraviolet radiation, generate powerful stellar winds, and end their lives in supernovae. This activity is great for enriching the interstellar medium with heavy elements, which are necessary for rocky planets, but it's not so great for habitability in the short term. Too much radiation and too many supernovae can sterilize nearby planetary systems before life has a chance to take root. So in the bustling, inner regions of a superspiral, particularly the starbursting arms, habitability may be compromised. These zones are dynamic and dangerous, filled with high-energy processes that can strip atmospheres, bombard surfaces with radiation, and trigger extinction-level events. For life to thrive, it needs stability, and that's harder to find in the crowded, luminous centers of superspirals. However, these galaxies are huge, and that works in life's favor. Their massive disks stretch for hundreds of thousands of light years, meaning they also contain outer regions, further from the dangerous galactic core and intense star-forming zones. These galactic suburbs, much like the solar neighborhood in the Milky Way, might offer safe havens for life to emerge and evolve. Here, older stars shine more gently, and the density of nearby supernovae drops dramatically. It's in these quieter outer arms where Earth-like planets might enjoy billions of years of relative peace. Another factor to consider is metallicity, the presence of heavy elements like carbon, oxygen, silicon, and iron. These are the building blocks of planets and, presumably, life. Superspirals are not only massive but chemically rich, thanks to their ongoing star formation and supernovae, which continually seed the galaxy with metals. That makes them ideal places for rocky planet formation. And since some of these galaxies are still relatively young, they may still be in the prime of their planet-building era. In fact, one could argue that superspirals are some of the most efficient forges of Earth-like planets in the cosmos. They combine active star formation with high metallicity and enormous volumes of habitable real estate. Compared to dwarf galaxies, which often struggle to form planets due to low metallicity, or giant ellipticals, which have stopped forming new stars, superspirals offer the best of both worlds, raw material and creative energy. But there's another side to this story, the frequency of cosmic hazards. With so much star formation, superspirals may also host more gamma-ray bursts, black hole activity, and stellar collisions, particularly near the core. Life in such galaxies might be more vulnerable to sudden extinction events. This raises the possibility that while life may arise frequently in superspirals, its long-term survival could be threatened unless it resides in sheltered zones. This risk is especially relevant when we consider intelligent life. Developing intelligence and technology takes billions of years. On Earth, it took nearly 4 billion years from the origin of life to the appearance of Homo sapiens. If intense radiation or catastrophic explosions interrupt that timeline even once, it could erase centuries, or millennia, of progress. That means superspirals may host abundant microbial life, but perhaps fewer civilizations advanced enough to communicate or travel. On the other hand, superspirals may also offer advantages for advanced civilizations. Their vast size means they have access to immense resources, from solar energy to interstellar gases to planetary materials. A technologically advanced society could spread across multiple star systems with relative ease, and even use the galaxy's rotation and gravitational gradients to travel efficiently over vast distances. The concept of a Type II civilization on the Kardashev scale, a species capable of harnessing the energy output of a star, might find the environment of a superspiral especially conducive to galactic-scale expansion. Moreover, these galaxies might harbor multiple intelligent species, evolving independently in different arms, separated by hundreds of thousands of light-years. Over cosmic timescales, they could even discover each other and establish interstellar networks of communication or cooperation. If we ever detect a message from another galaxy, there's a good chance it might come from a superspiral, simply because they contain more opportunities for life to arise, survive, and become aware. And what about observing them? Despite their distance, superspirals are bright enough to be seen from billions of light-years away. If life exists in one, we might detect biosignatures or technosignatures, chemical signs of life or artificial structures, in their light. Instruments like the James Webb Space Telescope and future missions like LUVOIR or HABEX could one day study individual stars and planets in these giants, helping us understand not just what they are, but what they might contain. In the grand search for life in the universe, we often focus on systems like our own, modest stars and quiet corners of average galaxies. But perhaps the real abundance lies elsewhere. Perhaps the universe's most active cradles of life are not in galaxies like the Milky Way, but in galaxies that are bigger, brighter, and far more fertile. Superspirals may be cathedrals of chaos, full of radiation, collisions, and violent births. But within those vast, spinning halls, there may be islands of tranquility where life takes hold. And if life can survive there, amid the glow and fury of a galaxy that defies logic, it suggests something profound, that the cosmos is not just hospitable to life, but overflowing with it, waiting to be discovered in the brightest spirals of all. In the vastness of the cosmos, where chaos is the rule and collapse is the trend, superspirals stand apart, not by defying gravity, but by mastering it. They are not loud in the way supernovae shout or black holes swallow. They are not the fiery screams of cosmic violence, but the graceful hum of balance stretched to its limits. They do not fight the laws of physics. They dance within them, at the edge of what's possible. Most galaxies begin in turbulence, and most end in silence. Spirals fragment. Ellipticals swell. Starbursts blaze and then fade. But superspirals, these impossibly vast, shining pinwheels, seem to have found another way. They do not rush toward collapse, nor do they burn out in youthful excess. Instead, they endure. They spin. They shine. And they hold their form even as their arms stretch across millions of light years. They are not just massive, they are deliberate. Their rotation curves stretch impossibly far, defying expected velocity limits. Their disks are not fragile. They are reinforced with dark matter scaffolding that stabilizes their structure. Their arms are not smeared into oblivion by time or turbulence. Instead, they maintain elegant spirals, like brush strokes across a canvas of dark space, painted not with ink, but with stars, gas, and cosmic light. And unlike the galactic giants we expected, spheroids, ellipticals, featureless and dormant, these are rich with life-making elements, steeped in star-forming fury, and cloaked in gravitational harmony. They form stars with reckless energy and yet remain calm, orderly, beautiful. They are chaos-tamed galaxies that say, there is more than one path. And sometimes, the path less taken is the most breathtaking. What do they tell us about the universe? They tell us that our models are not complete. That nature isn't interested in fitting inside our boxes. That for every rule we derive from light and math, there are exceptions hiding in plain sight, glowing brighter than we thought possible. They tell us that evolution, galactic or biological, is not linear or singular. It is multifaceted. Spirals do not have to become ellipticals. Growth does not have to mean disorder. Magnitude does not demand madness. They offer hope. Because if structure can survive that long, at that scale, then perhaps order isn't doomed in this universe after all. Perhaps the story of entropy has more footnotes than we imagined. Perhaps beauty, balance, and longevity are not flukes, but outcomes of a deeper resilience built into the very laws of physics. They are, in every sense, outliers, statistical anomalies that shouldn't exist in great numbers, and yet do. They lie on the fringes of scaling relations, on the periphery of our expectations, and in the glowing overlap between science and wonder. We found them only recently, and we have only begun to understand them. But already, they've expanded not just our knowledge, but our imagination. Because in these spirals, so vast they could wrap around 10 Milky Ways, so bright they outshine quasars, we see that the universe is still full of surprises. That the cosmos is not finished creating. That light can organize itself, persist, and last, even when gravity conspires against it. So as we scan the skies for more of these giants, we are reminded of something quiet and profound. In a universe ruled by entropy, superspirals are elegant outliers, cosmic giants that spin against expectation. They are the exception that proves the beauty of the rule. The silence of deep space is broken not by explosions, but by the whispering arms of galaxies too grand to fade. And somewhere out there, in the darkness between stars, they spin still, unchanged, undeterred, and utterly luminous. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.